Hi everyone. Thank you for braving the rain. So while we wait, maybe the last few people to trickle in, a couple of practical announcements. So let me remind you of the program of today. We are going to have our scientific program and continue until lunchtime, and we will also offer lunch to all of you who can stay here, that don't have to rush to the airport or something like that. Lunch won't be in the garden, it will be through this courtyard in the other building up the stairs. There will be signs. Same thing for the coffee break. Another thing that I wanted to remind some of you is that if you are reimbursed by cost, you have received, when you got invited to this meeting, you have received a link through which you can fill in your reimbursement form, and you also received, I think on Friday, an email with instructions to do so. So please try to do so in the next few days. Finally, another thing, if there are several people that need to leave, let's say either immediately after the talks or immediately after lunch, lunch will be from, let's say, 1 to 3 or something like that. We can try to arrange some shared transportation directly from here to the airport. Typically, each car would be something like 80 euros, a van maybe slightly more. So if it's group or like 5 or 6, it might be much more convenient than walking under the rain to the bus station and taking the bus. So how many people are leaving around lunchtime, either just before lunch or just after? You want to raise your hands? Okay, there are a few. So if you want to come see me during the coffee break, we can try to arrange something, and we'll figure it out. Okay, that's so much for the announcements. Are there any practical questions about announcements, other practicalities? Everything clear? Okay, so let me give the word to our chair for today, Diego.
Thank you. So welcome everybody to the morning session of the last day of the conference. Today we start with Ruth Brito, Constructing Amplitudes. So please take it away.
Okay, great. Good morning. It's great to be here. Thanks to the organizers for inviting me to this event, and thanks to all of you for showing up promptly after a festive night. I've been working in the realm of scattering amplitudes in a rather traditional sense, sort of in the context of relativistic particle scattering. So I'll talk a bit about my point of view, and what I mean by constructing amplitudes is finding ways to compute them that bypass the complexity of direct integration of the loop integrals. So the idea of bypassing this has been popular and implemented at several levels over the decades, and the common element is to find, this is what I'm calling a construction here, from some kind of ansatz or basis. And it depends then on understanding how to construct such an ansatz or basis to pinpoint the amplitude, eventually the numbers for the cross-section that you're going to need if we're talking about particle scattering. So some examples of this are, let's start with classic unitarity methods. So unitarity is a very big keyword, and that comes from the unitarity of the scattering matrix itself, related to the well-known optical theorem, which implies a relation to cuts, meaning an operation on the diagrams where some of the virtual lines are put on shell. This led to variations of this, which were more powerful. So besides taking some on-shell constraints that are directly related to the unitarity of the S matrix, what happens if you start putting more of the legs on shell? So this is called generalized unitarity, not really generalizing unitarity itself, but generalizing the on-shell condition. So these are called on-shell methods very broadly, and this allows you to put down more classes of constraints on your original ansatz or basis. Some modern terminology that comes attached to the same idea is now the symbol bootstrap. So bootstrap also, right, this general idea of constraining some kind of ansatz, and the symbol is going to be particular to Feynman integrals. This is different from the symbol we heard about yesterday. I'm coming to that shortly. So the key message that I want to convey this morning is that this all comes down to controlling the space of functions. And when I started in this field, then I would give talks, and usually some older members of the audience would say, yes, are you working on, or coming back to the analytic S-matrix, the old program from the 60s, in which it was hoped that everything would be understood just from analytic properties of the scattering matrix, including unitarity. And that's not wrong. We have been in the business of rediscovering, reinterpreting many of the old ideas, and we've made good use of this classic book. I just excerpted one figure chosen fairly at random to illustrate that it's full of the discussion of analytic properties. So you're looking about curves and sheets and really high-level complex analysis. And okay, so analytic properties provide enormous constraints, but on what functions? And I think this is the big difference between the program of the 60s and what we're able to do now. Is, for example, they'd consider a simple, simple 3-point, three-point function, the scalar triangle integral. And so the diagram I've taken here, figure from the book, has to do with some singularities, following singularities of such an integral onto different sheets. And again, this is not entirely obsolete. It's still, if you write down a formula, we still have to understand how to analytically continue it to different kinematic regions of interest. But my point is that the people working on the analytic S-matrix, they never wrote down a formula such as this with all the logarithms that make it so useful. And yes, it's these logarithms that have this analytic structure we see on the left, or an enclosed form hypergeometric functions such as this. So there are a couple elements here. One is that in the analytic S-matrix program, everything was completely generic, and they would talk about being in different dimensions, but it was understood it would be integer dimensions. So one big difference is now we understand it's very convenient to work in dimensional regularization, because masses are also not generic. In real life, we need to deal with a lot of massless particles. That's what we get in high energy collisions. So therefore, what I've highlighted here, this is a specific example which would not really have been considered. The fact that, so I'm just using the heavier lines to indicate massive particles. So here's an internal mass, and here's one with p² non-zero. The others are massless. So there's just a p² and an m² in this expression, which are the p² and m², of which this is a function. So this is a bit more particular. If you really had generic masses, there would be a function in terms of hypergeometrics and polylogarithms. It would be a bit more complicated than this, but we could write it down also. And working now in dimensional regularization, so this epsilon here, this is the parameter of dimensional regularization. So it's important to be able to pull that down out to do a series expansion and to read off the coefficients. And so, inevitably we encounter ultraviolet and infrared divergences that will be controlled, and we just have to understand how to control them. And I think really crucial to all the success of recent decades has been finding or understanding how logarithms end up in here, and more generally polylogarithms. So the logarithm and the dilogarithm shown in the previous slide, those are examples of polylogarithms, this larger class of iterated integrals defined here. Okay, so now the symbol that we're talking about is a symbol that really goes along with polylogarithms and can be defined for some classes of iterated integrals more generally. So by now there is such a thing as symbols for elliptic integrals as well. So from the form of the iterated integral, there's a way of reading off symbols. And here's just, in the faint gray, an example of what a symbol might look like. And Symbols are very useful because they encode basically all the relations that we know among logarithms and polylogarithms. For example, this is not quite the famous 5-term identity, but here's an identity involving the dilogarithm. And there are more, and the point is you can have these, especially when you write them in terms of more general z's, you can write down all kinds of relations. But the relations really boil down to if something is going to be equal to 0, so then you can easily collapse it, map it onto something that you can manipulate algebraically in tensor algebra, and find that's 0. So from this relation, you might still conclude, it doesn't follow directly that if a symbol of something is 0, that the thing itself is 0, but if you test some numerical points, you'd find that this indeed is identically 0. And the fact that the symbol is 0 is already telling you that you're pretty close to an identity. This is useful for Feynman integrals because many Feynman integrals are polylogarithmic, all at one loop and many even at higher loop order. Okay, so back to the idea of a construction. So symbols are very useful for construction. On-shell conditions probe the discontinuities at singularities. That's what you are measuring when you evaluate that integral in which you put some things on shell. So this can be interpreted as a discontinuity across a branch cut or an imaginary part of an analytic function. And discontinuities also expose the symbol structure very nicely. We've said, unitarity methods are the idea of finding coefficients of a basis of some known, what were called master integrals, distinguishing by projection onto cuts. So if you have different sets of edges, which are subsets of the edges of your original graph, then they'll have some on-shell conditions in common. So both discontinuities and differential operators are very very naturally connected to the symbol in this way that I've indicated here. I haven't said yet what delta is. Delta is a coaction, another algebraic operation, which basically corresponds to the symbol once you iterate it as much as you can. What it's saying is that on symbols, if you take a discontinuity on the function, what you get is the same on the symbol as if you take the discontinuity of just the first part of the symbol. And for a differential operator, it's the complementary condition. You only need to differentiate the last part of the symbol to get the result of the differential operator. Now, our current state-of-the-art methods for evaluating multi-loop integrals, there are different kinds. By the way, I'm referring to very large bodies of work here without any references because there are simply too many, but there are throughout the talk. There are some that rely on unitarity methods, which are essentially cuts, and some that rely on differential equations, some that combine both, and so for both of those kinds of operations, it's very helpful to know that they work well with the symbol. This is, I guess, one aspect of it that I personally have been involved in. So if you want to understand what the symbol of a Feynman integral is, I've just shown one example. You might take a coaction of a certain 2-loop integral. And with my collaborators, we've outlined, I guess, a proposal that you could do this at the level of diagrams too. That you can evaluate such an integral in terms of polylogarithms, and then you can compute the symbol. And we claim that would be the same as if you do an operation at the level of graphs first, and then expand the symbol. And this can give you some information about how the symbol is put together. That's what I mean by saying physical considerations, meaning the diagrammatic structure constrains the structure of the symbols. And what the graphical operations, so what we've done here is we start with some graph, and in the first part, the part that will still, on which you'll be taking further discontinuities, you get integrals that are related by having the same edges or some subset of internal edges. And in the second part, the part on which differential operators will act, you get naturally cut integrals. That's what these red lines are indicating. Those are the ones that are being put on shelf before you evaluate them. So I've shown a two-loop example to be fancier here. One loop is under more control. So at one loop, in the generic case, you can actually then read off what the symbol would be. So we have, that's coming back to this expression I showed earlier, we have sort of three representations of the same concept. We have a Feynman diagram written as a graph. You can evaluate it in dimensional regularization in terms of a hypergeometric function, or you can expand it as a series expansion in the dimensional regularization parameter, giving the logarithms. And so they give three versions of this coaction, which can be expanded into a symbol for the polylogarithms. And all these coactions, indicated by delta, they all have a common structure, which is, if you represent something as an integral, which is a pairing of an integrand and an integration contour, then you get two items in the tensor algebra, and they're related by changing the differential form and the integration contour in a specific way. So these integrands are related by integration by parts identities, and here you just have to find a set of new contours. What I want to come back to is the idea, we need to understand the space of functions, which might be polylogarithms, but which polylogarithms? It's these ones. This is really what I mean by the space of functions. If you start with your integral, how do you meaningfully expand it? By finding the basis, in math terms, a basis of cohomology and homology, to fill out is what you could call elements of the period matrix. This is the space of functions that you want to have control over.
What are the differential forms?
Well, it would start with the integrand of the Feynman integral. It's determined by the propagators for the internal edges. There might be some numerator as well. Okay, so I'm just summing over I, so there is some basis. So I said, for a real Feynman integral, an actual Feynman integral, you would find those in practice by applying integration by parts identities, and it turns out that this, the space will just close. They do have some finite dimension, and now we understand what the dimension should be. Okay, so that was the more general part. Now in the final portion of the talk, I want to come to the way in which I've been exploring the function space of Feynman integrals more recently. I've been looking at a way to actually change these integration contours by studying the on-shell conditions without momentum. Actually I should come back to, this formula here, where we change the integrands and the contours, this really corresponds very clearly to what we're doing here. What you get by integration by parts relations are the first entries in which you've changed the set of propagators, sort of sweeping the numerators under the rug. They can come along for the ride. And the second part, where you change the integration contours, that's really when you put things on shell, you can interpret that as taking residues, if you like, or in some way changing the integration contour of the original integral. So it's really just that. Okay, so I've been looking at, one way of presenting a Feynman integral, you can do them directly in momentum space. You can also use Feynman parameters. So this is a representation in terms of Feynman parameters, where we have the well-known Semantic polynomials, graph polynomials that you read off from the parameters. You have one for each edge. Of these two polynomials, all your kinematic dependence is in one of the polynomials, which is the F polynomial. And if we're looking for discontinuities, we're interested in discontinuities as we vary the kinematic parameters. So we're really focusing on F. Here, this integration domain, as we set up, use the Schwinger trick to introduce Feynman parameters, is given by having all the alphas non-negative. So the boundaries of the integration region are alpha I equals 0 for each I. So my proposal and what I've been investigating is the idea that cut integrals can be obtained. And so in this representation, you can't put p squared equal to 0 because you've integrated out p squared. You're left with some alphas. But I claim you can still find the on-shell conditions by changing this gamma, by changing the nature of the boundaries, by removing the boundaries for the propagators that you're cutting, and instead also including f equals 0 as a boundary. The justification for this idea comes from the Landau conditions. I wouldn't say this is quite proof yet, but actually you can make a cleaner argument based on discontinuities in different kinematic regions. So the idea is the Landau conditions are what led us to be looking at cuts in the first place. Landau basically wrote down two conditions for finding singularities. So if the inverse propagators are given by this capital AI, mass squared minus momentum squared for each propagator with an I epsilon prescription. These are the two Landau conditions. For each edge, the parameter times this inverse propagator has to be 0, and then there's something else for each loop. Now you can follow these conditions into parameter space. After you integrate out momentum, you can write them, and that were written in this form in the analytic S-matrix book, that you have, f equals 0 becomes one of your conditions. Alpha, some set of alphas have to be 0. That sort of follows from this condition, right? Either the edge is on shell in the momentum sense, or the corresponding alpha equals 0. And then, depending on which alphas are 0, for the ones that are non-zero are not necessarily 0. You still have some conditions on the derivatives, which then turns into a condition on the derivative of f. So I'd like to interpret these Landau conditions now in terms of boundaries of the integration region in the spirit of expanding the space of functions. So we can draw some pictures. This is for the triangle integral, but now that's not this triangle. These are, the triangle integral has 3 edges. So I've taken, alpha 1 equals 0 is this hyperplane, alpha 2 equals 0, alpha 3 equals 0, the 3 hyperplanes, and then there's a projection. And this gives you, so this is the integration domain, the standard simplex for the original Feynman integral. And then for the other cuts, I identify some other regions which are bounded by f equals 0, which is a quadric, an ellipse or a hyperbola, usually for a one-loop integral. And then you just choose some subset, or you identify some subset of these bounding hyperplanes to give you the new integration contour. What can you do with this? Well, one thing you can do with this is you can identify linear relations. It's in more technical terms, a statement that's true in homology, but you can just draw it as an inclusion-exclusion argument on these regions in parameter space. And what this gives you is that the uncut integral can be expressed as a linear combination of the cut integrals, which is a relation we were familiar with, but has a pretty complicated derivation. And now in this picture you can see it. You can see it very easily for any one-loop integral, just in terms of finding the regions. So you can select a basis of the function space, and I'm interested in pursuing this idea for more general integrals. So the vision, as coming back more generally, is that function space needs to be managed more generally. Maybe not everybody's working on Feynman integrals. We have amplitudes in different kinds of theories. I know you have functions in different kinds of theories. Sometimes we have some things in common. For amplitudes, I mentioned symbols have been very useful, but we're actually still at the point where we know the symbols are there, we can do things with them, we can build unitarity methods, there are improvements in differential equations. There's still a lot of room for further improvements. Many of us are interested now, to what extent can we fully predict symbols of amplitudes? This idea is what goes now by the name of the symbol bootstrap. What exactly are the arguments of the logarithms, and in what order can they appear? More generally, we're looking ahead to elliptic polylogarithms, other families, iterated integrals more generally. I also know that in many contexts, which are quite different from this, which maybe you encounter in your own areas, hypergeometric functions come up over and over, and there we have nothing like the symbol, nothing that gives you control over relations. There are many representations. We know there are many relations, and I would find it very useful, and maybe some of you would as well, if there were some theory, something even helpful like the symbol that would allow us to tame the complexity of relations among hypergeometric functions to help find a basis. So to close, I just wanted to say, control of polylogarithms has paid off richly. We built upon that a lot in the last decades for multi-loop amplitudes, Feynman integrals. Even in those cases, we do want better control of the symbols. Key concepts that we can take farther beyond polylogarithms are iterated integrals and these kind of periods, just constructing integrals for our functions by looking at contours and differential forms and how they work together. And just specifically, my idea that everyone is welcome to work on specifically as well, I can share some of the open questions, is to look at periods with parametric contours for Feynman integrals. Thank you.
Thank you very much for the nice talk. Questions?
For the second part of your talk, when you had this integral representation in terms of these Feynman parameters, those two functions which appeared inside this representation, those relate to the semantic polynomial. Do you assume, for this construction, do you assume that one of these semantic polynomials is positive definite in the physical region of the moment or not?
That would be the starting point, but it doesn't have to be. Yeah, so...
the reason I'm
yeah,
asking...
go on. Yeah, so here, okay, for example, what I've drawn here, this would be in what we call the Euclidean region. So there, a priori, you're integrating over that triangle in the middle, and the ellipse is, well, that's f equals 0, so f is positive inside and negative outside. But I guess, what I didn't show here for lack of time is you can try to follow the shape of that curve into different kinematic regions, and you can see, well, in this case, you can see very explicitly how you pick up discontinuities. So actually, no, it's more the opposite. If you're looking for a cut, so here, let's just take this one, for example. So here's a region which I've identified as a cut of one propagator. But that's not really where it comes from. Where it comes from is I would start in the kinematic region where there's a discontinuity in that mass. And in that region, f equals 0 would slice through the triangle. And because I'm interested in picking up the discontinuity, I would actually be integrating over the part of the triangle where f is negative, because that's where the discontinuity is. And I'd set up an integral there. And then, really my claim is that I can analytically continue that integral now back into the Euclidean region and interpret it as this one here. I don't know if that was...
One of the reasons why I'm asking, because some time ago, when people are looking for the semantic polynomial, etc., they figure out there is yet another source of singularities, so-called global singularities. Those which comes from a certain situation when you have this function f, which is not positive definite in the physical region of the momenta.
Mm-hmm.
So my question was more like whether you cover these additional singularities, which are, they're kind of very special. They're not universal. It depends on which process you're talking about, but they appear in general from the contribution when f, this semantic polynomial, is not positive definite. There's some hyperspace in this parameter, Feynman parameter space, on which this polynomial could change sign.
Okay, well, I'd be interested to look at that further, but let me say again that since I'm always setting up a region that's bounded by f equals 0. So actually, when I said that I was integrating in the region where f is negative, then I actually integrate minus f to some power. I set up a well-defined integral there, but f is not changing sign because the f equals 0 is a boundary.
More questions? Well, if not, let's thank Ruth again. All right, and our next speaker is Gregory Konchensky on proving quark confinement with energy correlators. Please take it
Thank
away.
you.
It's fine if you use that.
I shouldn't go far away from it. Okay, I understand. So first of all, it's for me a great pleasure to participate in this meeting, and I thank Alessandro and all organizers for setting up this nice conference. And let me say a few words before I will come to the topic of my talk. So I don't need to remind you that we're talking about fundamental changes in theoretical physics. And if you're thinking about those challenges which stay with us for the last decades, there is one particular problem which I'd like to draw your attention. And actually, this problem appeared one of the millennium problems, which we put forward some time ago, which goes under the name of the proving confinement. And I believe this is a very fundamental problem, which will still in the center of development in many years to go. And more or less, the question, the kind of provocative question which I would like to put forward is what did we learn about this problem over the last few decades of development of DSCFT and studies in subconformal gauge theories. At the end of the day, we are here just to solve challenging problems of theoretical physics. So we have some experience over a few decades of development of strongly coupled theories. And basically, the goal of my talk to show that in some situation you could profit from the knowledge which you acquired over the last few decades to solve really practical questions which has to do with the phenomenology. So the goal of my talk to show that there is very concrete phenomenological problems which goes under the name of energy correlation, which you could get hint of using this machinery which you developed using superconformal gauge theories. And what I'm going to talk is based on some joint work done is together with Dima Chicherin, Emily Sakachev, and Alexander Zhipoyedov, and I invite you to look for that paper for the further details. So let me introduce you in the field which we're going to discuss. So I told you that we're going to talk about confinement. Confinement is synonymous that we have a problem in QCD. And the problem goes as follows. When you formulate QCD Lagrangian, and it's formulated in terms of macroscopic degrees of freedom with quarks and gluons, and we know how to do theoretical calculation framework of those microscopic degrees of freedom. But when you come to the experiment, what you actually observe is not those degrees of freedom. What you observe is the bound states, hadrons. And this mismatch between microscopic and microscopic degrees of freedom, which poses a lot of problems. Just to make it very concrete, let me show you this cartoon, which more or less indicates what goes on at LHC. So in LHC, you have two beams of protons which colliding, producing many very energetic particles, quarks and gluons. We start moving apart. How does it? Yeah, they start moving apart until they separate sufficiently fast so that corresponding energy becomes small. And at that moment, hadronization phenomena kicks in, which converts quarks and gluons into hadrons. And once you look for microscopic distances from the collision point where your detectors, colorimeters are located, what you detect is not the quarks and gluons by hadrons. And fundamental question which people asked many years ago, given the fact that there is this phenomena of hadronization, how can you make any prediction if you don't control this transition, hadronization transition between two processes? So one possibility is self-confinement, and clearly we're not there yet, but there is another proposal which actually already existed for more than 4 decades, which is, goes under the name of quark-hadron duality. And the idea is quite simple. The idea is that is to define certain set of the quantities, observable quantities, which are called inclusive hadronic observables, such that computing those quantities short distances, which means in terms of quarks and gluons, you're expecting to get something which will match experimental observations up to corrections which will die out if you go to the limit infinite energies. So those observables, the inclusive hadronic observables, in general have this form. So you have some quantity which calculated at large energy scales, Q square, and you're expecting that computing this quantity in perturbation theory, dealing with quarks and gluons, expanding in power of the effective coupling constant, which is alpha s of Q square, which famously has property of decreasing at large Q square, would allow you to get some reasonable prediction up to some corrections, which goes under the name of hadronization corrections. And as I repeat once again, those hadronization corrections for this class of the observable are expecting to vanish as inverse power of larger momenta. So now let's be more concrete. Let's go to LHC and see what actually happens at LHC. you look for a particular event, and what you see here, it's actual event which has been taken by SMS collaboration. You could see there is some stamp indicating exact locations and point time, which shows you what actually observed at LHC. So what observed at LHC, here you have the special points, and these points, when two collision beams, which are orthogonal to the plane, collide, so there is some collision point, like Big Bang. A lot of energy is deposited at that point. You have production of many, many particles which start flying away. So you see all these green tracks. These are particles which move away until they approach some microscopic distances. When all those colorimeters are located, the colorimeter detect different parameters of the particles. So they detect direction in which particles moves, and they detect the energy that particle deposed in those colorimeters. So what you see here, so those rectangle of different color, the shape, the area of the rectangle corresponds basically the energy which was deposited on this colorimeter. So now if you look carefully at this picture, you will see that you have many, many particles produced, but those particles have a tendency to be kind of organized in a very special way. So you have a bunch of very energetic particles which have kind of collimated beam. So those collimated beams of particles whose momenta aligned all in direction are called jets. And then what you see on this picture, it goes under the name of the multi-jet final states. So in general, any typical event in LHC, you have a lot of particles which form jets, and what you observe in the final state, something like this. So now, following the philosophy I presented you previously, you want to find some class of the observable which would be able to compute using available technique, which would allow you to characterize this particular event. And there is many different proposals, different observables, and the one which I will be concentrated on is based on very simple observation that energy is a very good quantum number. And you could see there's a lot of energetic particle deposit. So let's think about this picture as if you were talking about correlation of energy deposited in different locations on the circle, and you could think about this circle as like cut of the sphere. So imagine you have some sphere surrounding your collision points, the detect is everywhere, the particles fly away, they deposit the energy, you know in which direction energy goes, and you're asking the question, what is the correlation between energy deposited in different points on this celestial sphere? So this observable is exactly what we're going to discuss, energy-energy correlation. So energy-energy correlation have been introduced in QCD back to 78. And once again, these are very simple observable, which has very simple physical meaning. Observable, which measures the correlation of energies deposited in different points of celestial sphere, so depicted here. So you're thinking about this picture, so here on the gray blob, Big Bang happened, so there was some collision which released a lot of energy, particles flying away. So you go on some microscopic distances, and you're asking the question, what's the correlation between energy which was deposited in particular direction over here, direction over there, so there's an angle between these two directions defined by some variable chi. So in practical terms, the quantity you're dealing with is this energy-energy correlation, which depends on the relative angle between detected particles, which obviously runs from 0 to pi. And if you want to compute this quantity, which goes under the name of EEC, or energy correlation, you have to look for a quantity like that when the first factor is differential cross-section, another way, probability to create particular final states with the particle distributed in a funny way. And you put inside this differential cross-section this special factor, which measures the energy deposited in the colorimeter under condition that the amount of particles which enter colorimeter is separated by the angle chi. And capital Q is the total energy center of mass energy. So they're very simple observables. And once again, if you just follow this idea of quark heteroduality, what you will be doing, you will be computing this quantity in theoretical QCD in terms of the quarks and gluons, and you will be comparing this quantity to observation which is done in terms of the hadron. And if you believe the quark heteroduality, you're expecting to find that for sufficient large energies Q, this calculation you did in the theory should match observation done by experimentalists, provided the energy is sufficiently large. So this quantity have been measured quite intensively over more than 4 decades, starting from DAISY machine and then later at CERN lab machine. And here I'm just giving you a cartoon of the measurements which were done for not the final state which I presented previously, but the final states corresponding to E plus or minus annihilation. So you have E plus, E minus electron positron, which annihilate producing a virtual photon, which in the final state decays into the hadron, and you're looking for the correlation of the energy deposited by the hadron on your celestial sphere. So we have very, very precise experimental data, and those data shown here on this plot. So let me explain you what's shown here. So on the vertical axis, these are this quantity which I introduced you, energy correlation. On horizontal axis, I plot cosinus of the separation angle, which always can run from -1 to 1. So this one corresponds to the angle being 0. This -1 corresponds to the angle being pi. And what you see here, black dots, they correspond to the observation data points taken by Delphi collaboration in the time. And what you see here, like red points, those come from the prediction made in QCD. And QCD prediction, it took some time actually to compute those predictions. So the first calculation, lowest order coupling constant, was done back to 78. Its coupling constant defined as some scale Q, times some function A, which you explicitly know. And then you could see it took 40 years to do the next order calculation. And the reason for this large time gap is not because people are stupid, because calculation is very complicated. Then if you're brave enough, you could ask the question, what will happen if you continue further? And you do have to continue further, because if you just see on this plot, you will see that the accuracy, theoretical accuracy actually is much better than theoretical uncertainty. So if it took 40 years to go from one loop to two loops, you could estimate how much time it will take to get the next loop. And what does it mean? It means that actually we have to develop much more efficient way to do the calculation. So this calculation, which were done both at one and two loop, were based on the standard techniques, based on static amplitude. And more or less, you see these techniques reaches its limit, and you have to do something else. And actually, one of the things which happened over the last few decades, that people indeed found the way how you could do the calculation, not in QCD yet, but in kind of cousin of QCD theory, which we all love, which is NFL4 macrosymmetric Yang-Mills theory. I will explain you later what was the magic there, but let me just emphasize that right now in this particular theory we already have 3 loop results, so this correction is known. And we have a prediction at strong harmonic as well. So let's now, excuse me, one thing which I forgot to mention, sorry, to go backward. Yeah, one thing which I forgot to mention, what's special about this picture? So you have this picture which has very characteristic shape. You see it's kind of function which is peaked around the endpoint. So why it's peaked around the endpoint? So let's look on the horizontal axis. So you have cosine of the angle, -1 and 1. So let's first think about this point. So -1 corresponds to the correlation angle being pi. And the fact that function is shaped around this point is synonymous. The corresponding final state has very special form. It has only 2 jets which go back to back, and clearly the most energy which will deposit in the final state will correspond if you put the detector back to back. And this is the reason why this function is peaked around these special points. But now you go to the opposite limit, this limit. So it corresponds to the chi going to 0, which means we're talking about correlation of the energy within particles belonging to the same jet. And it will be this region which we're going to investigate. And the reason why it's peaked here clearly is that you have very energetic jet. If you're looking for correlation of particles within the same jets, jet very energetic, you expect it to have some enhancement, and this explains why this peak appears as well. So in general, such kind of picture, even if you didn't know what was calculation behind, looking at the picture, you immediately conclude that you're dealing with 2-jet event. And now imagine if experimentalists did their measurement and they found something which were flat. So imagine instead of have this function like that, you will have just constant value. What does it mean? It would mean that it doesn't matter how you put colorimeters, the energy doesn't depend on the angular distribution, which means that energy is homogeneously distributed on the celestial sphere. So therefore, this shape of this function automatically gives you information about how the final states look like. So what I'm going to do, I want to concentrate on this particular region. So we're going to discuss the region when we're looking for the inside the jet, and we try to find the correlation between particles within the same jet. Why? Because in this way, energy correlation will give you some information about how actually the jet is organized. So how does the jet rise? So I already sketched the mechanisms. So you start with energetic particles, for example, quark, which was produced at short distances, and then it flies away, producing a lot of radiations, quarks, gluons, which at some moment get hadronized, and then they reach colorimeter, and you measure the correlation between hadrons located within the small jet, with the corresponding angle between n1 and 2, there's a vector defining the position of a colorimeter of celestial sphere separated by angle chi, and we're going to look for the region when chi is small. So once again, you turn on this philosophy, you want to compute this quantity perturbation theory. So you compute the perturbative expansion and pass with the coupling constant, and then you're hoping the hybridization correction will be small. So then let's look what we expect from this perturbative piece. So perturbative piece will describe this branching process. So you have quark going into bunch of gluons quarks, and so that invariant mass, so the jet which produced, has characteristic energy which scales like center of mass energy multiplied by the angle chi. So if angle chi is small, invariant mass also gets smaller. And if you do the calculation, you will find the corresponding probability, the corresponding contribution to energy correlation scales as inverse angle. I remind you, angle is small, in some power which is 2, it's like kinematical power, minus some anomalous dimension which you compute order by order in QCD. But what's important that if you look for the argument of coupling constant, since it runs, it defines on the scale which is Q, large scale, times the angle. And once you have such kind of behavior, you immediately realize that something goes on. Namely, if you go to extremely small values of the angle, so that Q times angle becomes of order lambda QCD, coupling constant blows up. What does it mean? That means the perturbation theory indicates you that some new physics, non-perturbative physics, will appear for the angle of order lambda QCD divided by Q, which is small, but still it's there. So now let's ask the question, what actually happens based on experimental observation when you approach such small value of the angle? So obviously you expect the perturbation theory will not be applicable, so you're entirely in a perturbative regime. So how does this function will look like if you really go to that small region? And this question has been addressed recently by people which you see here on the slide. What these people did, they looked for the so-called SMS open data. So this is the data we could find on the internet, and then you could compute any observable you like using those data, and they use those data to compute energy correlation. They look particularly into this region. So let me explain you what you see on this plot. So once again, on horizontal axis, you have angle. So this is angle chi, which I introduced previously. Notice this is logarithmic scale. And the vertical axis, they put so-called normalized EEC. Normalized, it's, if you translate into my notation, it means that we have this EEC we've seen previously, you multiply by chi square. So this chi square slightly modifies the behavior, which we will discuss in a second. So what you see in this picture, and once again, these are experimental data. These are what experimentalists measure. So what you see is that if you start from some relatively small values of the angle, you see 10 minus 1. So you have something which has very smooth flat behavior, and then you go to very, very small values of the angle, you hit exactly the value of the angle when you expect the perturbative physics kick in, and indeed there's some transition region after which the shape of the function changes. So once again, these are data, and this data know about non-perturbative physics. So now let's try to decode this non-perturbative physics into something which I told you previously. So first of all, let's take, please.
So you said that that's an experimental result. I mean, is there any way to be sure that this region of quarks and gluons is there? Can you directly or indirectly know that there are?
Forget about what's written there. Forget free hadron transition for this interpretation. So these black crosses, this is experimental data.
Okay.
What's written above is the interpretation of those data.
Yes.
Okay? So let's distinguish two things, data and interpretation. What's shown here, this is data. Now you have to interpret this data using what you know. And as you could guess, what's written above, this interpretation, this region which is shown here in blue, could be interpreted in terms of the perturbative QCD, quarks and gluons. Then there is this transition region which corresponds to hadronization. This is exactly the region when you quarks and gluons get transformed into hadron. And then if you go to extremely small values of the angle, this becomes entirely an non-perturbative region when you're not even allowed to talk about quarks and gluons, you talk about hadrons. Okay? But now if you remove this chi square out of the definition, if you draw this figure slightly differently, just taking out chi square, what you will find that these two different regions, blue and green one, have different behavior as a function of the angle. So this part, which seems to be like a linear rising function, after you take out this chi square, actually becomes flat. So this behavior, this region here, from point of view of energy correlations themselves, correspond to the flat region. Flat region, I remind you, the distribution celestial sphere full of the energy, there is no jets. And now if you go to the region which is here shown in blue, which seems kind of flat, after this chi-square removal, it becomes actually a region when energy-energy correlations growing. So you clearly see that non-predictable physics leads to these two different regimes, and there is some transition between two regimes, which happens exactly for the values of the angle which I spotted you previously. Now the question, could we explain this transition and the underlying mechanisms which are responsible for the change of the behavior if you go from perturbative to perturbative cascade? And my point, which I'm trying to convince you later, that physics behind this transition has to do with the fact that you're dealing here with a big number of particles produced. Another way, we knew from the very beginning that LHC, you have a lot of particles produced, a lot of multiplicity of particles. And now the idea is that let's take this fact for granted and let's try to use multiplicity of particles as the new expansion parameter. Another way, what I want to do, I want to expand my energy-energy correlation in inverse powers of multiplicity. To do so, I have to come up with some model. So let's start from the simple model. And the simplest model you can consider free scalar theory, no interaction. So how could I get large multiplicity? So I start with some operator, which is phi in power k, and I excite vacuum with this operator. What will happen if I excite vacuum with this operator? I obviously produce k scalar particles, which go in the final state with no interaction. So you could ask the question, what would be the contribution to the energy-energy correlation in this situation? So you look for correlations of energy correlation between, let's say, m different detectors, and one, etc., and m direction of the celestial sphere. You look for the differential cross-section producing big number of particles in final states, and you compute this integral of including differential cross-section, including some additional factor indicating the particles go in direction defined by the colorimeter. So it's already at this level, computing this integral is not simple. But if you go to the limit when this k, I remind you, k is the number of particles in final state becomes large, you will see some remarkable simplification. So you have final states which has total energy, capital Q, and you're producing a lot of particles. Sum of energies of those particles should be equal to Q. But number of particles is infinitely large. So what does it mean? It means each individual particle will have infinitesimal momentum, infinitesimal energy. So if you rescale energy appropriately, you will find that in terms of those variable epsilon, which I put here, the corresponding integral of phase space of many particles actually simplifies enormously, and you get at the end something which looks like ensemble of particles whose energy is distributed according to this exponential law. But most remarkably, if you're thinking about how does dependence on the angle enters, you could explicitly check the dependence as angle suppressed by the multiplicity. So what does it mean? It means that if you go to the limit where multiplicity goes to infinity, you will get in the free series the result, which looks like this. So some kinematical factor, 1, no dependence on the angle, and dependence on the angle becomes suppressed by 1 over k. So you have, roughly speaking, situation which we've seen a strong coupling. The dependence on the angle appears suppressed by small parameter. And indeed, what happens that some time ago, Hoffman and Maldacena, they looked for energy correlations in strongly interacting angle for theory, and they found that in the limit when coupling constant goes to infinity, using calculation of strong clapping from a DSFT, they found that energy correlations have exactly the same behavior. Namely, in the limit lambda goes to infinity, energy correlation approach constant, and all dependence of the angle suppressed by 1 of the lambda. So in both cases, you have more or less the same behavior. So there is no jets, energy is homogeneously distributed in the celestial sphere. My mechanism is different. In the first case, in the case of free scalar theory, it was due to the fact that we produced a lot of particles and we went to the limit when number of those particles is infinite. Whereas in the second limit, you start from finite number of particles, you turn on interaction, and because interaction is infinitely large, it immediately populated your phase space with infinite number of particles. So these are different mechanisms which at the end gave rise to the same final states. Please.
Well, the formula is two different. One is 1 over lambda, the other is 1 over k.
Yes, because once again, this formula 1 over k, it was obtained in the limit. It was lambda equal to 0, but k large. So you have function which depends on two parameters, coupling constant and k. Now I'm asking the question, what will happen if I go for this function to two different limits? One limit, I fix lambda and I send k to infinity. And another limit, I fixed k and I send lambda to infinity. These are two different limits. I'm saying in both limits, you get the same result. Tolini coda. indeed. But next step, we will address the question what will happen at the level of those suppressed correction. But the stance right now, in the limit when k goes to infinity, lambda finite, and lambda to infinity k is fixed, you have the same result. And I said mechanism is completely different. So now let's turn interaction, right? So now we want to deal with our theory, doesn't matter, QCD, scalar theory, whatever, and now you have to find the way how you could compute these energy correlations in interacting theory for arbitrary value coupling constant. Obviously, this is a very complicated issue. And the way how you could address the question, you have to go away from perturbation theory. You don't want to have something which is intrinsically perturbative. And to do so, you have to rely on yet another formulation of energy-energy correlations, which was developed a long time ago, which is based on very special operators, which are called energy flow or energy flux operator, which defined here. So you have stress energy momentum. You look for the projection of stress energy momentum in a particular direction, and you do some stretch manipulation. So you're integrating over time, and you send special coordinates infinity along certain directions and put in front some factor r square. So what's remarkable about this operator, if you take matrix element of this operator with respect to some particular final states, you will see that the matrix element will pick up exactly particles which go in the direction defined by vector n, and they give you a result which exactly the one which measures the energy flux in this direction. So once you have this operator at your disposal, you could show that energy-energy correlation for any value of the coupling constant, which is given by Fourier integral like that. When you have two operators OK, those which producing your final states with large multiplicity of particles. In previous case, it was 5 power k. And now you have insertion of two additional operators which are there to mimic colorimeters. So these two operators effectively measure the flux of the energy in the direction of N1 and 2. So now once you have a definition of operators, etc., you combine them together, this becomes kind of very complicated formula you have to deal with. But what I want to emphasize is that if you just take away the integral, what stands inside, you have 4-point correlation function, and let me find these are Weidmann correlation functions. This is not the one which you get used to, the Weidmann correlation function. Operators are not ordered, which involves 4 operators. Two of these operators are heavy because you have final states with large multiplicity, and you have two stress energy tensor. So at that moment, you see that the next step to compute energy correlation, you have to provide information about 4-point correlation function involving two stress energy tensor in two infinitely heavy operators. And this quantity is exactly the one which you start analyzing using IDS-CFT setup. So what could we say about this function? So at this moment, okay, we don't have much information except for n equal 4 theory. Let's concentrate on n equal 4 theory when you have this powerful technique which I described previously. And then you have a lot of things like comes as a bonus. The first things, because you have maximal supersymmetry, you could show that this correlation function which you need, the one which involves, the one which involves two heavy scalar operators to two energy tensor, but the Bokafur-Watt identity is related to a much simpler function which involves only half VPS operators with different weight. Two of them are light, two are infinitely heavy. And this correlation function has been studied quite extensively in the literature, and we know by now this correlation function in n equal 4 theory up to 3 loop at V coupling, and we know also at strong coupling, including corrections coming from supergravity and the strings. Hopefully, in some nearest future, we'll know it's for any values coupling constants and integrability, but for the moment, let's concentrate what we know. So now what you do, you combine information that you have, so you plug in into this formal expression for 4-point correlation function n equal 4 theory, and you go to the strong coupling, this limit which I mentioned previously. So you go to the limit when lambda goes to infinity much faster than k. K is multiplicity of particles produced. And then you recover Hofmann-Maldazzini result, which is the one you see here. So I remind you it was a constant plus terms which one over lambda suppressed, and here you have very explicit expression which involves dependence on the angle. So z is related to the angle variable. And as I already emphasized, if you go to the limit lambda to infinity, this term goes away and you have constant distribution depending on the angle. But now let's go to the opposite limit. So let's go to the limit when lambda is fixed, and let's send k to infinity. Then you could show that for any value of the coupling constant, which is finite, which means much smaller than k, this energy-energy correlation has a form which is constant plus 1 of k times multiplies the function, which itself depends both on the coupling constant and angular variable. So this function is kind of new ingredient. But what's important, this function comes with 1 over k, so therefore you have more or less the same feature as before. But now let's look for this function f. So this function f could be computed at weak coupling because we have quite a number of information. And let's see how this function looks like if you go to the limit when variable z goes to 0. So now we're zooming into the region when we're talking about correlation between particles within the same jet, the small angle limit. So you have your perturbative expansion. So these are Born level contributions, which we already knew was a constant. Then you have 1 loop corrections, 2 loop corrections, and 3 loop corrections. So now if you go to the limit, z goes to 0, even though function is quite complicated phi by 3z, for small z they simplify. For example, this function becomes 1 over k, 1 over z. So these 1 over k factors in common. You have 1 over z coming from here. You go to 2 loop, you find 1 over z log z, some enhancement by log. And then you could show that if you continue further, this log will exponentiate. So the final expression will look like that. So you have constant term plus something depending on the coupling constant, 1 over k, and z in some power, which also depend on a. So this result was obtained using the coupling expansion. And then you ask the question, what will happen if you go to arbitrary value of the coupling constant? At that moment, you have yet another powerful method, which based on so-called OP expansion of celestial sphere, which was developed in parallel. And if you follow this OP analysis, you will find what you expect in general based on general ground. This function f, of which energy correlation, should have a form like that. So you have identity operator contributing, which gives you 1, and then you have contribution of some so-called special light rate operator with certain quantum numbers, and their contribution scale with the coefficient function, which has this form, z in power 1 minus anomalous dimension divided by 2. Now if you match what you have in perturbation theory and what you have here, there is perfect match. Namely, you could deduce out of these two formulas anomalous dimension at weak coupling, and also you could deduce the matrix element which stands here in the numerator. Actually, it scales like 1 over k. This information is sufficient to explain the physics. So now let's take this formula and try to understand how does this formula looks like if you now go to different limit. So let's first take z fixed. So I look for the fixed angle and I send k to infinity. Then what you're expecting to find behavior which is 1, flat, no dependence on the angle. It's exactly what happened in this hadronization region, which was a region for extraordinary small various angle. But now what will happen, I fixed k and I send z to 0. Then this exponent in the denominator will dominate and you will have power-like behavior. So these two regimes, which you see in experimental data, naturally appear if you start from this very simple expression for this energy correlation in terms of this matrix element. So in this way, you went through this long procedure, we exploited different results coming from different fields, and finally we got something which conceptually looks similar to what you find in the experiment. Moreover, this formula also tells you that you're expecting to find the transition from one region to another for very special values of multiplicity, which scales with an angle like that. Basically, that's it. Let me conclude. So what I did, as I promised you, we started with some phenomenological observable energy correlation. So we started looking how we could compute it using different techniques. So we looked for simplified version of QCD and equal force theory. We found that using various kind of techniques, you could get this very interesting behavior at small angle, which seems to match what you observe in QCD, namely existence of these two different regimes for small angles and hadronization phenomena, etc., etc. And last but not least, what this analysis shows you that if you're thinking about studying scattering amplitude, physical cross-section, etc., it seems like there is yet another parameter which appears on top of all others which we discussed so far. It seems like number of large particles, number of standing legs, could be used as yet another parameter, playing with which you could exploit yet another properties of the observable. This is basically home-away message, which I believe is important in view of the potential application of the formulas for another observable. Thank you very much.
Thank you very much for the, thank you for the very nice talk. Questions?
So, Grisha, did the people try to get this energy correlation in the simple phenomenological model where the jets are being formed by fragmentation of string splitting?
Yeah,
There's no relation to QCD at all.
I didn't say this, but if you look for this slide which I have shown you, this one. So what's shown here, these dots. So this lower panel, see this lower panel, it tells you difference between, let's say, series experiment. And you see there is different color. So different color corresponds because what people are doing now experimentally, they simulate final states using different partonic branching. Another way, you start from the final state that has the quarks and gluons, and then they use different hybridization models which convert quarks and gluons to the hadron, and they just doing this kind of phenomenological calculation using different hybridization models. Hopefully that you're supposed to get, oh, excuse me, sorry. Hopefully that you should get the same result, and basically you see that all these curves, they more or less look the same. This is more or less a posteriori proof the different partonic branching models that people used, different models. Lund hadronization, string hadronization, whatever. They give more or less comparable results in this case. But also notice that there is somehow, so this one is synonymous of saying C is equal to the experiment. Deviation from 1 means there is some non-P2P correction which you don't control. And you could see there is some contamination corrections around 1 and around 0. So I talk about this region. And you see that this picture already suggests you there's some non-P2P physics goes on in this region. This is basically what I was trying to explain. And there is yet another part, and this part also is worth exploring. And there are some interesting results coming from this region, which also could be interpreted in terms of some conformal data, etc., OP, which I didn't have time to cover, but I could give you references if you're interested in it.
Thank you. More questions?
So everyone's favorite 4-point function has also been analyzed from the point of view of localization by these integrated correlator guys. So can you somehow reverse engineer that integration to sort of extract information?
As a matter of fact, good question. So this formula, this correlation function which I appeared here, sorry. Sorry. Yeah. So you see that here you have correlation function of HVPS operator with different weight. So the question is, what could you say about this correlation function? In principle, to compute energy correlation, you have to know this correlation function as a function of all coordinates. Recently, there was a lot of activity about computing so-called integrated correlators, which is another way of saying you start with this correlation function, which function of two cross ratios, and you integrate it over cross ratio with special measure. And this way, you're losing dependence with the coordinates. You're getting again something which function of coupling constant only. And then you ask this question, could you do inverse engineering? Another way, using information about integrals to go back and reconstruct dependence on the coordinates. The answer was no, for arbitrary value of the coupling constant. But a strong coupling, it's possible. A strong coupling, you could use information about the correlators to reconstruct coordinate dependence of this correlation function. And actually, this formula which you see here, excuse me. So this formula here, it was obtained using exactly this input. But in general, it's it's open question. Whether you could use information about integrated correlators, and there's many different, not only these integrated correlators, there are some other integrated correlators you could compute, whether you could use this information to reconstruct correlation function itself for arbitrary value of the coupling constants. I think these are very interesting questions, but as I told you, well, as far as I know, it has been answered only for this particular limit lambda to infinity, but in principle, these are very interesting questions to explore.
So on one of your slides, it was written that those energy correlators, they do not suffer from infrared divergences. Yes. Why is that?
Where do the infrared divergences come from? They come from the emission of particles with small energy. So imagine you're emitting particle with small soft energy, infinitely small energy, and you look for the contribution of this particle to your observable. So you have differential cross section, you have to integrate over variable phase space, and imagine if you have some soft particles in the final states, normally it's producing you logarithmic singularities. Another way, infrared divergence will appear like integral the epsilon over epsilon of the energy of soft particle. But once you go to energy-energy correlation, you will multiply this differential cross-section by the weight factor corresponding to the detection of this soft particle. And the weight factor comes with the power of the energy. So therefore, you start from the integral, which was the epsilon of the epsilon, logarithmically divergent. You multiply by the epsilon, you get something which is infinitesimal, which is physically means that if you have particle with infinitesimal energy, they don't produce any contribution to something which is sensitive to the energy of produced states. But this question is more deep than you might think, because what people experimentalists like, they like measuring various kinds of correlation. For example, not only energies, but for example, you have particles, hadrons, which are observed. They have various quantum numbers, including charges. And then you ask a question, could it be possible to measure not the energy correlation, but correlation of charges? Because these calorimeters, if you remember, at the beginning I've shown you a picture with so there was different rectangles. So different rectangles on this plot, they correspond to computing different quantum numbers. One of them is energy, another is charge. And then we ask the question, is it possible, they measure correlation between charges with experimental data. Then you ask the question, is it possible to compute those correlations between charges using perturbative Kosekin framework? And you will find you're not, because these charge correlations, they're not infrared safe. They suffer from infrared divergences. And the reason for this is also quite obvious, because before I told you that energy correlation is special because they come with additional factor of the energy. But now imagine you have in the final state particle which has infinitesimal energy, but charge 1. You still have integral with respect to the epsilon of the epsilon, but doesn't matter how small the energy particle is, charge is 1. It doesn't depend on the energy. And that's the reason why this particle will produce infrared divergences. And infrared divergences in perturbative integrals is synonymous with this quantity actually is sensitive to physics at large distances. So it doesn't fall into the class of the observables which I defined previously, those when you're expecting the perturbative corrections being suppressed. So therefore, message of this, that if you define different observables and you want to play this game, you have to be sure the observables called infrared safe. In other words, in perturbative expansion, you don't encounter any contribution coming from large distances. This is so for energy-energy correlations, but I give example of quantity which is not. And in general, it's open question, which is discussed by various people in different community. What will be the most general class of those infrared safe observables which could be measured and computed simultaneously?
Okay. Thank you.
Any more questions? Well, if not, we can thank Gregory again.
So, quick announcement. Those of you that are leaving from here and want maybe to get a cab to the airport, please come talk to me right now and we'll try to arrange something. Everybody else, there is the coffee break. It's going to be across the courtyard up the stairs, and you have a guide. There are also signs. I'm sure you'll find your way.
if I...
Use this one, but you move farther.
Okay. Do you think I should?
All right, so maybe we can start with the second half of the morning. We have Michele Del Zotto talking about generalized symmetries. Please take it away.
Hello. Yes. Okay. So thank you very much. Thank you very much for the organizers to invite me to give this presentation here. I was asked to give an overview about recent progress in generalized symmetry. So that's what you're gonna get. Apologies if many of these things are things that you have already heard. I will try to give some overview that leads to the most recent developments. So the final part of the talk will cover things that have been developed over the past year. So yes, thank you again for having me here. It has been really a pleasure to meet with all of you, and congratulations for this action. It's really exciting. Generalized symmetries. Well, we know since a long time that quantum field theory have extended operators, and that extended operators are interesting. They give they are order parameters for confinement, for instance. And the generalized symmetries, this generalized global symmetries, is essentially a framework to try to express what are the conserved quantum numbers of extended operators of quantum fields. No? This was developed more or less a decade ago, by these gentlemen. And I mean, the idea is essentially how do we generalize an ordinary symmetry of a d-dimensional QFT? An ordinary symmetry charges points by linking them with a symmetry operator, and shrinking the symmetry operator by a contact term, we obtain the action of the symmetry on the point-like operator. The symmetry defects are essentially discontinuities in the field space that leave correlators invariant. No? Now, how do you generalize this if you have an extended operator? You have an extended operator, the support is not a point, it's like a line, a surface, or a membrane. No? And this action is like a linking action, so we can introduce a sphere that links the defect, and again, parameterizes this discontinuity that leaves correlator invariant. No? And this linking action is essentially the one that one obtains from higher p-form symmetries that have been introduced a decade ago. No? Examples, if you need a reminder, a well-known example is given by Maxwell theory, where we have the Wilson lines and the 't Hooft lines. Wilson lines are defined as holonomies of the Maxwell field. The 't Hooft lines are defined in a slightly more complicated way. You can remove the line and prescribe a monodromy of the field around it, such that it carries the linking sphere carries a non-trivial Chern class. No? And again, from the Maxwell equation, we see that there are two higher form symmetries that are in the Bianchi identity. There are two higher form symmetries that are conserved, and out of those we can build these operators that again have a depend only topological on the linking sphere because of the Stokes theorem. Essentially, these are higher forms. No. So this is an example of a theory that has this linking action, and I think that I want to stress is these symmetries in Maxwell theory are spontaneously broken. This was a result that I learned from Gaiotto Capuzzi and Simon Reville about a decade ago. No, and the photon is the Goldstone boson for the spontaneously broken one-form symmetries in Maxwell theory. It's a very interesting remark. No. So the masslessness of the photon is a consequence of this fact. I remember I was really, I got like shocked with this result. It took me years to recover. But I think that I want to stress is that these generalized symmetries also have more charges. No? On top of this linking action that we see here, there is a crossing action. So whenever topological defects intersect the word volume of extended operators, they can give rise to a finer actions and more charges. So there is not just linking, but there is also crossing. No? This effect is known in the condensed matter literature as symmetry fractionalization. No? So these generalized global symmetries are understood in terms of a topological subsector of the spectrum of operators of the quantum field. Topological here is in quotes because the dependence of symmetry operators on the support is topological up to contact terms with charged operators. No? That, like, they are topological as long as you don't cross something that is charged. No? And in that case, it will induce a discontinuity in the field which carries the symmetry action. And as we have seen, they have they give rise to word identities, they give rise to selection rules like ordinary symmetries. No? How do you get a selection rule out of a topological operators? Well, an example is by using topology. No? So for instance, here I draw a sphere with a pointer operator inserted. This is just like this operator is extended. I'm just drawing it as a point here, but it extends in other dimensions. No? What matters is that there is a topological defect with respect to which it is charged, and there is a non-trivial topology there. No? So I move the defect around this sphere. I shrink the operator. I get the action of the representation. I can move it also in the other direction, and if I move it in the other direction, because of the topology, I can shrink it down to nothing. It doesn't wrap anything. It disappears. No? And so I obtain a relation between the two correlators, one on the left-hand side, one on the right-hand side. If this representation is non-trivial, no, this implies that this correlator is 0. No? This is how we get selection rules out of topological defects. No? This is an example. And if you consider a partition function on curved space-time, the type of identities that you can get are more and more complicated. No? You can exploit the topology of space-time to fold these topological membranes on themselves and obtain more interesting relations and constraints on correlators. So these are features that like generalizes features that we know from ordinary symmetries. But there are also, and again, also spontaneous breaking is another feature that we know it has, but there are also other features. No? Other features, the most salient one is that there is a fusion product. So these are, you can think of these topological defects as literally topological membranes that support some topological field theory on top. No? And when you bring them together, they give rise to a fusion. It's just the tensor product of the two theories. No? They are tensor product them. So if you have a group like symmetry, then you stack them on top of each other and you get group multiplication. But if you have more general topological theories, then you can get a fusion product where you have more summands there. So something that does not have a trivial group structure, something more general. No? One remark here is that there are only positive integers in the right-hand side, and this follows from locality. No? So if you consider a space-times, you have a time direction, and the time direction selects your quantization. So for every transverse slice, you can assign a Hilbert space. And if you insert the operators only along space, you get symmetries that act on the Hilbert space. But you can also insert them along time. And if you insert them along time, well, that changes the quantization. No? So it changes, it gives you twisted boundary conditions for your Hilbert space, defines twisted Hilbert spaces. And the fusion rule that you get has to be compatible with this. So it has to be compatible with the fact that you have to interpret the fusion rule in terms of twisted Hilbert spaces. And like, while we know how to add the integer copies of Hilbert spaces, we don't know what is a half of a Hilbert space. No? And so this is a deep constraint that arises from locality. No? Like the fact that there are these twisted Hilbert spaces implies that you can only take direct sums here, essentially. No? So this is just to stress that the fusion product that we get is really very constrained. Whenever you come up with these topological membranes, you have to check that this really works, that the fusion coefficients that you obtain are really integers, positive integers. No? This is very non-trivial. And moreover, there is this feature which we call a Higher structure. So let me remind you what the idea is about the Higher structure. This extended defect can form junctions. No? On top of stacking them, you can just deform them, bring them together, no? And they join. And after they join, they fuse. No? So of course, like if you now start bringing in more and more defects, they can fuse in multiple ways. No? So here I have three defects, no? D1 and D2, they fuse, they become D1 tensor D2. I bring in a third one, and they become the product of 3. But there is another order in which I can perform this operation. No? I can start from the first one, and I can start from bringing together the second and the third one. I get the D2 tensor D3, and then I bring in the first one, and again I go into D1 tensor D2 tensor D3. No? And so you see, since this is topological, I can deform one of the first type of collision into the second one. No? And this associativity condition is encoded by a defect of a Higher codimension. No? So associativity, which for groups is very, very straightforward, in this case becomes a feature. There is a way of decorating this associativity with further data. And this data is further data that enhances the symmetry structure. So an example of symmetries that have this feature is given by Higher groups. No? So Higher groups have been introduced at I learned from Cordova Dumitrescu and Intriglietto in 2016, but they were around in string theory for a long time before that. There were gauged versions that were constructed to speak about Ramond gauge fields in string theory. No? But in this case, these are global. They are not gauged as they are in the string context. And so what happens? Let's consider the two groups as an example. You have a zero-form symmetry. These would be codimension 1, D1, D2, D3. They would be codimension 1 symmetries, which are labeled by a group element. And then you have a one-form symmetry, again, labeled by a group that I'm calling A. No? So the crossing action is just the fact that if I take this codimension 1 defect that carries the action of the group G and I move it across the codimension 2 defect that correspond to the one-form symmetry, then I can multiply it by an automorphism. No? I can represent the action of the group G on the group A by an automorphism of the group. That's the crossing action. No? And on top of that, you see there is this associativity. I can call this G1, G2, G3. I have the products, no? And there is the associator. Because these are groups, the only possibility here is given by a cohomology classes, called a Postnikov class. And that is what enriches the structure of the symmetry. I don't just give you G and A, the zero-form symmetry group and the one-form symmetry group. I have to tell you how one acts on the other, this automorphism, and the associativity, what parameterizes the associativity, no? Which is this twisted group cohomology class. This is all explicit and all computable. You can compute it in examples. And it has some phenomenological application. And in particular, for me, it was interesting that all this data has to match across duality. So this enhances duality constraints. No? Like we exploited it to probe some features of little string theories, and because little string theory happened to have these global Higher group symmetries, Lee Homori Tachikawa used it in the context of cyber duality in 4 dimensions, and this gives a new constraint on possible dualities among theories, the matching of Higher group structures. But let's go back. So the idea is, okay, we have this fusion product, this Higher structure. And so, like, in a sense, this indicates that the structure of symmetry is not just parameterized by groups or Higher groups. There is a further generalization which is given by symmetry categories, like the various interfaces that we have are defining Higher morphism in a Higher category. But since I only have 20 minutes, I don't want to there is a lot of formalism that is being developed to describe this, but I won't say more than that. Instead, I want to say, yes? Do you take the effects to be always static or let them move? This is an important distinction. No? All these defects are topological. No? So they are defects in my quantum field that I can wiggle at no cost. They don't have displacement operators. No? So that's why they give rise to word identities, because I can just bubble one out of nothing, no? Move it around my correlator, cross charged operators, transform them, and then make it vanish. No? And all these processes give rise to word identities, like for extended operator insertion. So this is literally like asymmetry. No? Thank you for the question. So now I wanted to discuss a way of building some of these operators that don't transform like group, that they are more general than Higher groups. No? So this happens because of a remark, which is if you have a finite symmetry and you gauge it, gauging a finite symmetry is a topological operation, topological manipulation of the field. No? Gauging a finite symmetry doesn't introduce any new degrees of freedom. No? It's really something very elementary on the field. No? And so you can, by gauging a finite symmetry over half space, you can build interfaces between a theory T and a different one, which is that theory where you have gauged this finite symmetry. No? So this, in principle, now is an interface between two different theories. Theory A, the first theory, and the other one where we have gauged this symmetry. But it can happen that there is an equivalence, a duality, that relates the theory with the gauged symmetry with the theory I started from. And when that happens, we can compose the half-spacing interface with the duality and obtain a topological defect, because one is an equivalence, the other is this gauging of a finite symmetry, which is a topological operation. But now it is an interface, a topological interface of the theory T with itself. So it's codimension 1, and it fits the bill. It is a topological interface. And I compose them, I bring them together, and I obtain this interface. And you see, if I want to fuse it with its opposite, the opposite is like the dagger in this context. To obtain the dagger of a topological membrane, you just consider the orientation reversal of it, and you stack them together. So if I do it with this duality defect, you see that I can separate the green surfaces which correspond to the action of the duality. I compose them. I compose a duality with its inverse. I get back to the identity, and then I'm left with a region where I'm gauging this finite symmetry A. This is still topological, so I can smash it, and I obtain a fusion rule where I have the fusion of this duality defect with its conjugate that becomes equal to what? To a surface where I have gauged the finite symmetry. So this is an example of a non-invertible fusion rule, because this is not the identity. I'm taking a topological membrane, I'm fusing it with its opposite, I obtain something that is an operator which is not acting just as the identity. One remark is in order. This surface is porous. So gauging a finite symmetry corresponds to decorating a triangulation of my space with topological defects. And so since it's topological, I can always make it poke hole in it. And so a local operator would just pass through this interface. So from the perspective of local operators, this is an invertible fusion. It behaves like a unitary operator. But if you throw a line into it, then you cannot open this gauging surface in such a way that the whole line goes through. And so there is a way of detecting the non-invertibility of the duality defect, exploiting extended operators. So the constraints that you get are more interesting in that context. So again, example, our Maxwell theory has this stuff. So you can consider, I reminded you about the one-form symmetries of Maxwell theory at the beginning. We can consider gauging finite subgroups of those. If I gauge a Zn subgroup, for instance, of the electric symmetry, this has the same effect as just shifting the potential by an integer, changing the quantization conditions, and shifting the coupling as here. But Maxwell theory also has electromagnetic duality. And electromagnetic duality is an equivalence that takes Maxwell theory at a value of the coupling and maps it to Maxwell theory at a different value of the coupling, where I'm swapping electric and magnetic degrees of freedom. So in particular, so I have my gauging interface that has this effect on the coupling. I have electromagnetic duality that gives this. If I find a fixed point of this operation, then I can build I can build a duality defect like the one that I described in the previous slides. And so there are plenty of duality defects in Maxwell theory at special values of the coupling. So Maxwell theory is an example of a theory that has non-invertible symmetries. More example can be built exploiting class S theories, where again we have control over the electromagnetic duality, like in N equal to 4 Superior Mills. There are lots of families of models that have this type of features. I want to go on and just discuss briefly why we should care about Heidegger associativity. So you see, we discussed it before. If we bring 3 of topological membranes together, we get a codimension 2 interface. Like we go in this example of the figure, we have surfaces, lines, and a point. But if we start bringing in more, then we get interfaces that are smaller and smaller. So I bring 4 of them, then it becomes codimension 3, the places where the Heidegger associativity happens. And so you see immediately that all of these data give rise to extra data, like the case of the Heidegger group. All these Heidegger associators are extra data that gives me a finer structure of the symmetry. but it stops. No? Once you get to the point, once the intersection becomes smaller and smaller and smaller, and you reach a point, then you cannot go smaller than a point. Like it's a negative dimension. It doesn't make sense. So what do you get there? You get consistency conditions from Higher associativity. No? And these consistency conditions become obstruction to gauging when we cannot trivialize them with local field redefinition or counter terms. So let me give an example of this in quantum mechanics so that it becomes more understandable. In quantum mechanics, we know that the Hilbert space is in a projective representation. So this means that when I bring together two operators, I get the product up to a phase, no, a projective phase. These are unitary operators or unitary ones. We can try to get rid of this phase using local counter terms, which means I can redefine my unitaries by a phase that depends on the group element. When that happens, the projective phase transforms like this. I redefine my operators like this, the projective phase shift in this way. And so the question is, can I get rid of these phases? Well, associativity is a constraint, no? Like I have the associativity of the product happens only if these phases add up in this way, no? And so I have to solve, in order to understand whether I can trivialize it, I have to solve a cohomological problem. I have to consider a space of all alphas that satisfies this constraint up to this relation that is essentially a differential. And the class that I obtain is a class in group cohomology that is exactly the one that parameterizes the anomaly for quantum mechanical theories. No, it's the projectivity of the representation. No? So you see, in quantum mechanics, it works. The Higher associativity, which in this case is just associativity because quantum mechanics, the operators themselves are inserted at points, so there is no Higher structure there. But still, like you recover the anomalies in quantum mechanics from the Higher structure. You can do the same exercise in 2 dimensions. In 2 dimensions, the associativity is captured by F symbols. The constraint that they have to satisfy is this pentagon identity that I'm drawing here, but I won't explain. But just the same logic occurs. No, you have associativity, you have a constraint that is given by a Higher associativity structure. This gives a cohomological problem. You try to solve it. It's parameterized by a cohomology class, and that cohomology class is the one that captures the anomaly in the ordinary group case. No? So that's the logic that I want to emphasize. So we care about the Higher structure. We care about the Higher structure because it captures anomalies. And we know that anomalies are very important. If we have an RG flow that preserves the anomaly, it has to preserve the whole Higher structure. It has to preserve all this data. No? So this is, in a sense, why this categorical symmetry might give a finer lens to the infrared and to the dynamics of quantum fields at the bottom of the RG flow. If we can preserve them, then we get a finer structure that has to be matched by the infrared phase. No? So how do we capture this Higher structure? How do we compute it? No? One way is to use the word volume of the defects, like we do with membranes. If we want to understand when membranes form junctions in string theory, we study the word volume, we study the junctions. There are ways of doing that. And here, for the topological membranes in quantum field theory, we do the same. There are topological field theories supported on their word volume. But that's very hard to do. And so, if you happen to know what is the symmetry to begin with, there is an alternative way of capturing this topological defect, which is given by this symmetry TFT construction. It goes under the name of symmetry TFT. And the symmetry TFT consists in the following idea. You are interested in, say, in the symmetry of a given theory T, and you realized it in terms of a bulk boundary system in 1 dimension higher. So there is a topological field theory in, say, this theory lives in D dimension. The topological field theory lives in D+1 dimensions. And it has 2 boundaries. One boundary is gapped, is topological, so I can move it around without any problem. And the other boundary is a relative field theory. It's a field theory which is dynamical, and it depends like on the bulk. And since this boundary condition is topological, we can move it along this slab, no? Such that it gives an isomorphism between this D+1 dimensional system and the dimensional system we started with. No? So why this is useful? The idea is essentially that if you know what are the topological operators of this TFT that I call Z in this picture, then the one that survive against the boundary will capture the topological operator that live on my theory that I'm interested in. No? So whenever I can realize my theory in this form, then I know how to construct its operator, topological defects. Applications of this idea, well, the first one is that it really separates the data of the topological symmetry from the theory that I start from. This is essentially the analog of a representation of a group, if you like. The part that captures the symmetry is this one, and this isomorphism is the analog of the representation. No? This also streamlines construction of duality defects. One can, exploiting this formula, is one can construct duality defects in many cases in full generality. And moreover, it gives a generalization of 't Hooft anomaly matching constraints for higher phases that I will discuss in a second. One important feature of this is that this isomorphism allows to import all the techniques that have been developed in mathematics to describe topological quantum field theory over the past two decades into the description of topological defects of dynamical quantum field theory that are non-topological. No? This is like, I want to try to explain a couple of these points more in detail. So why do we say that it separates the topological symmetry data from the theory? So the idea is that if you have in my theory, remember at the beginning of the talk, we say that we have this linking action, no, of the defects. So here the charged operator is this red dot, and the topological defect is this green line. No? If we move it in the SimTFT, they call it SimTFT sandwich. You see that the charged operator is associated to a boundary condition for a topological line that stretches from the topological boundary to the relative field theory boundary. And the topological defect that give rise to the symmetry correspond to another topological defect in the bulk that survives along the boundary. No? And the fact that it survives means that when I close the sandwich through the isomorphism, I obtain this linking, but the whole computation happens in the topological sector. The linking happens in the topological sector. I don't need to go in the dynamical sector. It's captured by the topological field theory. No? So the action of the symmetry, the representation of the symmetry on the operator, is something that I can compute entirely in topological field theory. And then the non-trivial part, the fact that there is this isomorphism, is what says how to translate this non-trivial representation into a representation on the operators of my theory. No? That in this case would be boundary condition for this red topological defect that stretches from the boundary to the relative bulk. Another aspect that I wanted to emphasize in this talk was this generalization of 't Hooft anomaly matching. No? This is another very interesting feature. So since this bulk is topological, whatever happens dynamically, it happens on the right-hand side of the picture. So the RG flow is something that happens on the representation side of this figure. No? So like the RG flow from a UV to the IR is a feature of the other boundary, and this part stays put. So this is essentially the 't Hooft anomaly matching, if you like. If you have an RG flow that preserves the symmetry, it is compatible, it fits into a single SimTFT description. And this is interesting because this allows for an application to the dynamics of this infrared physics in terms, for instance, of symmetry-protected gaplessness. So symmetry-protected gaplessness, what is it? If you have a symmetry that is preserved along an RG flow, and this symmetry is anomalous, no? Then you know that the infrared of this flow will be degenerate, because in order to match the anomaly, you need a plurality of ground states, no? So if you have an RG flow to the deep infrared, there are two possibilities. Either you have a gapless theory or it is gapped, no? If it is gapped, you expect to be able to describe this degenerate ground state exploiting a topological field theory, no? So if there is no topological field theory that can support that anomaly, then you conclude that this symmetry-preserving RG flow must be gapless, okay? So this is this symmetry-protected gaplessness in a nutshell. No? From the perspective of the symmetry TFT, classifying topological boundary conditions that are symmetry-preserving becomes straightforward. It's a computation that is entirely topological. And so one can rule out. One can classify the boundary condition that preserves a given symmetry and rule out gapped boundary conditions. And therefore conclude that if you know what is the symmetry TFT for that symmetry, you know that you have an RG flow that respects it. Since the bulk symmetry TFT doesn't have the corresponding boundary condition, the endpoint of the RG flow must be gapless. So this is an interesting application of this effect to a deep dynamical question of the field theory, which is the gaplessness of the ground state. Finally, well, I wanted to mention a relation to geometric engineering and holography. No, so yes, I'm done. Yes. So like there are ways of learning about these symmetry theories from familiar construction in string theory. So we've heard in the past days about holography. Holography is a dictionary between an ADS gravitational theory and a conformal theory. I want to stress that like most of the holographic dictionary that we know give rise to relative field theories. So this was emphasized by Witten a long time ago when he was speaking about the global structure of the gauge group in holography. And so there is a way of reading off this symmetry theory from try to extract a topological subsector of the bulk ADS theory. And essentially that gives a plethora of examples and also tools to push this dictionary between symmetries and bulk boundary systems beyond finite symmetry, beyond the familiar symmetry theories. And also, like exploiting geometric engineering, give rise to ways of studying the word volume of these topological membranes in terms of word volumes of the familiar membranes in string theory construction, in which we take some topological limit. We extract some topological sectors. So a lot of work has been done in this direction. I just wanted to emphasize, since this is an overview talk. So as an executive summary, I would say, okay, there is increasing evidence that symmetries are captured by a topological sector of the spectrum of operators that is organized by a Higher category. The Higher structure of symmetry is interesting because it gives a finer symmetry data, and it captures anomalies and generalizations of anomalies that you can use to constrain RG flows. There is a formalism, this symmetry TFT description, that is a very convenient tool to capture this Higher structure. We learn how to use it. We learn about features of quantum field theories that would be very hard to extract otherwise. But this is just the beginning of a story. There are already some applications to the dynamics of QAT in terms of symmetry-protected gaplessness. And there are further constraints on the higher physics exploiting these things that are familiar in condensed matter, symmetry-protected topological phases or topological orders, that are now being imported in the language of gauge theory in higher dimensions. And with that, I thank you for your attention, and I conclude.
Thanks, Michele, for the very nice talk. Questions?
Thanks. In the first half of your talk, you said that if you have a topological defect, then because it's topological, you can always push a local operator through it. Mm-hmm. What's the argument for that?
He's a mathematician. The idea is if it is topological, it means that displacing it doesn't have an energy cost, no? So you can move it around your space-time without paying a price. And if your operators are inserted in correlators, you can and they are inserted at a specific point, and the codimension of the defect works out, then you can imagine sliding your defect in space-time in such a way that it crosses it. No? When it crosses it leaves out a little bubble around the defect, and that little bubble encodes the action of the symmetry on that charged operator. No?
More questions? Well, not, let's thank Mikel again.
Thank you.
All right, so our next speaker is Vasilis Niarchos, and he's going to tell us about quantum mechanics and deep learning. No? Take it away.
Okay, so it's a pleasure to be here. So I want to talk, this talk is mostly motivated by quantum field theory, in particular non-perturbative dynamics of quantum field theories is what I'm mostly interested in. This is a fundamental and still largely open problem. And I don't have to motivate, I think, a lot the importance of these problems in this audience. The ability to solve specific QFTs, gauge theories, for example, and discover new ones like non-Lagrangian ones that are more exotic is important for theory and applications. One class of lessons that we have been learning over the years is due to all sorts of different, very interesting dualities between different types of quantum systems. Dualities between quantum field theories and quantum field theories, or dualities between quantum field theories and gravitational theories like the ADS-CFT. This is very important because it teaches us a lot of new conceptual lessons. We get a lot of new conceptual lessons about what it means to do non-perturbative quantum field theory, but it's also useful practically because it gives a second life to perturbation theory. Now we can use perturbation theory in the dual description to extract non-perturbative information. But it's also true that in all sorts of, the large majority of dualities that we formulate, we rarely can go beyond the status of well-motivated conjecture, so we cannot prove them. So despite the significant and impressive progress, the available truly non-perturbative tools that we have available is limited. Here are some examples. Numerical methods like lattice field theory, this is usually what we have in mind when we say, oh, we'll take this theory and we'll put it in a computer, have well-known limitations and are intimately tied to traditional approaches. For example, we cannot use them to study exotic quantum field theories like the 6D 2,0 theory because there's no path integral, which we will compute with the lattice field theory method. Special tools like those based on supersymmetry, integrability, anomalies, have provided a lot of very interesting, beautiful, useful information, but do not allow us to have full access to generic theories and observables. Bootstrap methods that I will come back to are very, very promising. They are truly non-perturbative, but they are not yet at the level where they can solve an arbitrary theory. So this is basically the invitation part of my talk. So it's clear that we have been making a lot of progress, understanding all sorts of different non-trivial aspects of quantum field theory, but it's also clear that it is difficult to go beyond the state of the art. It is clear that we need new ideas. And that's the main question here is, can we think of new ways to solve quantum field theories? One, let's say, naive idea is maybe we can view QFTs as big data structures that can be learned. And this is exciting because basically of the particular circumstance of what's happening in computer science. In computer science, there is a lot of progress, all sorts of interesting, amazing things are happening. So it's natural to ask whether we can use them, things like, for example, from machine learning or AI to solve quantum field theories. And this also connects to Magdalena's talk. But here the focus is not so much on string theory, but quantum field theory itself. So, okay, so that's a natural question, but exactly what should we aim to learn and how? So here are 3 points. So one thing we can try to do is we can try to solve all problems in new ways. So for example, we can go back to lattice field theory and we can try to improve sampling processes, like use ML methods to do that, and this is something that people have been thinking about. Another thing that we can think about is what we can do with ML methods is to perform more efficient searches of solutions. When you have a large landscape of configurations and you search for specific ones and the search problem is very hard, ML methods have proved to be a very useful alternative. And for many examples in string theory, you can take a look at Magdalena's talk or Fabian Rule's review from 2020. Now, since the focus here is on quantum field theories, I want to highlight a particular direction, which we have started studying with Kostis Papageorgakis at Queen Mary, but it's basically quite an open direction yet. Like, how do we apply such methods in conformal field theory? In conformal field theory, in particular in the conformal bootstrap program, we can, basically what we're doing is that we're trying to find consistent CFT data. What are the CFT data? Scaling dimensions and three-point function coefficients. And we try to constrain them using principles of symmetry, like crossing symmetry, for example, or any other relation, generic relation that we have. And so you can think about it as some very complicated sets in the configuration space of all possible CFT data, and there you need to select the ones that are consistent. And this is precisely the logic that we try to follow with Kostis in a series of papers. And in particular, one of the things that we're doing there, we are exploring adiabatic deformations from tractable to intractable regimes, from weak coupling to strong coupling, tracking the evolution of solutions of interest across parameter space. And we use reinforcement learning algorithms to do that. The way we do it is completely different from the standard approach. Instead of making some assumptions that then we eliminate, doing the standard semi-definite programming methods, what we are trying to do is we are actually trying to truncate the spectrum, write down explicitly the crossing equations, do a careful, so we do not do hard truncations. We try to also estimate tails, etc., but we are actually trying to solve explicitly the crossing equations. And then we're doing a search on CFT data that will satisfy the equations. So doing things like this has the obvious advantage, it's non-rigorous, but has the obvious advantage that you don't need positivity. So you can apply this in many situations where the current bootstrap doesn't go, for example, in the case of boundaries or finite temperature or whatever. And one of the places where we got very promising results is this one, the last paper, where we applied it to the bootstrapability context. So we analyzed correlation functions on half BPS Wilson lines in N=4 theory. This method can reproduce, without using positivity, the same results that Nikolai Gromov got at King's, at the same accuracy, like at the accuracy for some data of the 7th digit, but with much, much less computational cost. For example, the standard semi-definite programming methods require digit precision at every step of hundreds of digits. They were using 1,000 digits. We did it with just machine precision, 16 digits, and we got the same results. In some cases, were even better. So the key question for the future in this context is, basically, in the previous slide, I was sort of critical about all these methods that we're using so far, that they do not allow us access, and now I basically want to turn it around. Basically, now it seems the key point for the future is, can we take all of these results that we're obtaining with special tools, in special corners, and then bring them together under some other strategy, more general strategy, that will use this specific information to make the searches more informed, improve the searches, and give us access to all the other data that we cannot access at the moment. And this is, in fact, I think the current trend in general in the conformal bootstrap program, how you inform the searches with the information you already have. Now, a third thing that you can do is you can try to learn new structures in some tractable corner. So you have a complicated problem, you can only solve it in some corner. And then there you can try to learn a new structure and then attempt to generalize it, generating new solutions in previously inaccessible regimes. Generalization is a central problem in artificial intelligence. And it could be very interesting in this context where also generative AI techniques might be useful. So in the rest of this talk, I want to stay with this third point, and I want to give you a very specific example of how, or one particular example of how one could explore this in a very specific, simple problem. So let me first explain this toy problem. So this is based on recent work with Kostis Papageorgakis that was recently posted on the archive. So let's go to, I will phrase it in the language of quantum mechanics. So we will consider elastic 2-to-2 scattering in quantum mechanics. And one of the things that we compute there is the differential cross-section. It is directly expressed in terms of the square of the scattering amplitude. The scattering amplitude depends on the scattering angle, theta. I will use z, which is cosine of theta. So experimentally, we measure the differential cross-section, and we learn about the modulus of the scattering amplitude, which is a complex quantity. Since it's a complex quantity, it has a modulus, it has a phase, and the very basic question you can ask is, if you have the experimental data of the modulus, can you reconstruct, say at fixed energy, also the phase of the scattering amplitude and therefore the whole scattering amplitude? So the two quantities, the modulus and the phase, are intimately related to each other. How do you know? For example, if you use a partial wave expansion, then you express everything in terms of phase shifts. And if you have the phase shifts, then you can take the imaginary part. You can take, you can compute the modulus, you can compute the phase, and everything is expressed in terms of the phase shifts. Now, this is easy to do if you have a finite partial wave expansion. So if you want, for our case here, this will be the tractable regime. You have a finite partial wave expansion, and you can analyze everything. The problem is much harder for generic amplitudes that have an infinite partial wave expansion, which is the generic case. This problem is not new. It was studied in the 60s and 70s when people were trying to analyze, as Ruth mentioned in the morning, the analytic properties of the S matrix by people like Martin, Atkinson, and others. And the standard approach goes like this. Again, as we heard in the morning, unitarity plays a very crucial role. So if you rewrite unitarity in this context, it gives you a direct relation between the phase and the modulus, and the relation is an integral relation of this form. It's not the worst relation you have seen, but it's not also straightforward. You can see that it's non-linear, it involves a double integral. Also notice that we integrate over zeta1 and phi1. Zeta2 is expressed in terms of z, zeta1 and phi1 in this way. So what people were doing in the 60s and 70s was to analyze this equation. So the analysis of this equation quickly yields some interesting results. For example, if I set z equals 1, then this factor goes. Z2 equals z1, so therefore the cosine also goes because it's 1. And there sine of phi is an integral, a double integral, or an integral of the modulus b. And since it's supposed to be a sine, it must be less or equal than 1. So if you give me some b that doesn't satisfy this inequality, I cannot solve the problem. Now, you can get additional bounds, for example, on existence and uniqueness of the phase. For example, if I define this function, which is a previous integral without the cosine, then I can take the maximum value of this function. It's called the Martin parameter. And for formal reasons, I denote it as a sine of a parameter mu. When the sine of mu is less or equal than 1, then you can show that you can find a unique solution. When sine of mu is greater than 1, solutions may or may not exist. When they exist, they can be unique or doubly ambiguous. And in general, it is unclear what happens. Okay, it's not an easy problem. Okay, so can we solve it? So that's the problem. First of all, what is the traditional way of solving the traditional thinking about solving this problem? Well, we can use ML, for example. And again, as you heard from Magdalena's talk, neural networks are good approximators of functions. So the unknown function, we're given b, so we need to find phi. Phi is the unknown function. We can use a neural network to model the unknown function. So we model phi by a neural network that has some parameters theta. We formulate a loss function, which is basically how well we satisfy this equation. And then we try to optimize the parameters of the neural network in order to satisfy, in order to bring this loss as much as, to make it as low as possible. So we turn this problem into an optimization problem. Finding the optimum neural network parameters is called training and involves solving a generally hard non-convex optimization problem. This is precisely the type of problem that recent ML progress has been able to solve. So this approach is called a PIN, a physics-informed neural network, and is a standard neural network method for solving PDEs. Here we're not solving a PDE, we're solving an integral equation, but it doesn't matter. This approach was recently used by Sasa Ziboevdov and collaborators to revisit this unitarity equation and solve it using a neural network. And they produced some very nice results. For example, one important question here is, I told you that for sign mu greater than 1, you have ambiguous solutions. You give me a B, I can find 2 Bs. And these are very special configurations. So you can ask, what is the smallest possible value of the Martin parameter where you can achieve these doubly ambiguous solutions? And the previous bound was, I think, sign mu, which was around 2.15. So these guys were able to find a new solution, new configuration, with an even lower bound, improving the bound after 50 years. Okay, also note that this approach requires retraining from scratch for each new input B that you give me. So every time you give me a new B, I have to solve the problem from the beginning, right? So, which is a time-consuming process. Okay, now, what I said is basically the description of the problem, but it's not exactly what I want to do. Remember, my point 3 was you have some tractable corner, you want to discover some new structure, and then you want to solve it. So here, the tractable corner is the finite partial wave expansion situation. The structure that plays a key role here is the unitarity equation. So I want to do something slightly more ambitious. So now we'll play a game where we assume that the unitarity equation is not known. Okay? In this problem, it's known, so we're using it as a toy problem, but in many other problems that we care about, we don't know that equation, and we want to discover it. So the only tractable information that we will allow ourselves to have access to comes from finite partial wave expansions. And the question is, if I give you only finite partial wave expansions, can you discover this equation and solve it? You're not allowed to use that equation, okay? Now, why is this interesting? Because more generally, because what I'm really trying to learn here is not model a function, phi of z, for example, but really learn a map, an operator, between two types of functions. So I'm really trying to learn maps between infinite dimensional spaces of functions, which is also interesting from a continuum QFT perspective, again, as we heard in the morning, because QFTs are naturally structures operating on such spaces. Like you take a path integral, you operate on functions. So understanding how to do efficient manipulations with functions or learning functions is important in general. Okay, so can we do this? And the answer is yes. So in computer science, there is a more general neural network architecture, which is called the neural operator, which does exactly that. In usual neural networks, you start from an x and you go to the function f of x. This is what you model. But here you have another architecture. I display it here with a black box, that starts from an input function or a set of input functions and go to a set of output functions. The architecture of this is more complicated. It's a more complicated architecture. It has linear operations. It has non-linear activations, but it also has integral transforms. So it acts non-locally on the space of x's. In this case, we are not supposed to have the equation, so I cannot put it in a loss. I can only do supervised learning, so I can show it a lot of examples. What kind of examples? The ones I have access to with finite partial wave expansions, where I show it a lot of B's and phi's, okay? And I train only once. Once I trained, I can use it to make predictions in less than a second, okay? Another cool feature that this has is zero-shot super resolution. In order to put it in a computer, I have to discretize the space of x's, or the z, here, okay? But this thing has been typically used to solve PDEs, like the Navier-Stokes equations. You can solve the problem, or you can show it samples in some low resolution, and then it will produce very efficiently predictions for higher resolutions. So this is called zero-shot super resolution. Okay, so let me show you some examples, and then I will conclude. So let's do that. So one of the things we did is we took one of these neural operators called Fourier neural operator, It does basically all these integral transforms in Fourier space. That's why it's called the Fourier neural operator. We trained it on 300,000 B5s, which consisted of 100,000 L equals 1 amplitudes and 100,000 L equals 2 amplitudes and 100,000 L equals 3 amplitudes. We had to use GPUs on a cluster to do that. And we discretized for this exercise Z on a uniform grid with 100 points. Okay, so we do the training. We reserve some data, some samples to do testing. And this is an example of of tests where you can see in orange and blue the prediction and the ground truth, and basically they're on top of each other. The accuracy is at the level of 1%. And so that's a signal that it has trained well, okay, on finite partial wave. Now, how does it generalize? That was the main question. That's what I'm trying to probe. How does it generalize? Does it allow me to learn about scattering amplitudes that have an infinite partial wave expansion, which is supposed to be the hard thing? And here are two examples, one with a linear B, Z plus 4 over 10, and one quadratic B, Z squared plus 1 over 2. We selected this because it's also what Zibouedov and company have as examples. And you can see again that they are on top of each other, so it has predicted well, okay? Again, at the level of 1% or 1,000. We can do more. We can do a scan, very quick scans, over lots of linear and quadratic moduli. This is the linear, this is the quadratic. And here, for the moment, I'm allowing myself to use the unitarity equation to see how well I'm performing. So you can see that I get lower losses precisely inside this I, which is precisely the region where sine mu is less than 1, which is precisely where I expect to find solutions. So these two plots, and everything is bad outside the dual bound. This is the dual bound, and these curves are sine mu equals 1. So it seems to be performing quite well, and qualitatively it has the right features, and I will show you later the corresponding plots with the pins of Zibouedov and company. Now, this is promising, but I cheated, okay? The first problem is that I told you I cannot use the unitarity equation. So if I cannot use the unitarity equation, how can I check that I made a good prediction? Also, in some cases, there should be no prediction because there's no solution. But the neural operator will be producing predictions. Another question is, okay, here in these examples, it seems that the neural operator performed well, but does it perform well everywhere? And you can check that the answer is no. For example, if you test on higher L finite partial wave expansions, it performs poorly. So it has learned something non-trivial, but not the complete information that the unitarity equation has. Okay? So I need more. What do I need? I need the ability to, I want the neural operator to rate itself, to be conscious of whether a prediction is good or bad. So here, we went a step further in a rather non-standard application of neural operators to do the following. So we do not only train the neural operator showing it what it means to succeed, but we also show it what it means to fail, okay? And that gives it the ability to learn both good and bad predictions. So let's redo the exercise. Now we train on 400,000 samples with the following composition, 225,000 true samples like the ones before, and 175,000 false samples. And when it makes a prediction, it produces a prediction for the phase, but also a label, like dog, cat, that tells you, is it a good prediction or a bad prediction? And when we train on the true samples with f equals 1, we call it a fidelity index. When we show it false examples, we set the label to 0. We find that we get much better reliability from F when we average over several neural operators. So the collective information from neural operators is a useful thing. This is also something that we learned in the bootstrap exercise with the reinforcement learning. We're getting better results when we had lots of agents exploring the landscape of safety data. Within the training data set, we also notice the following thing. What we mostly care about is how reliably does the neural operator predict that the solution exists. So this will happen when f bar, this fidelity index, is very close to 1. So let's say f bar between 0.99 and 1.01. Okay, it's very close to 1, so it's supposed to be predicting that it's a good solution. So in the test sample, how many times was this correct? How many times was it predicting a correct solution? It was actually a correct solution. The answer was 98.6% of the time. Okay, so we also find if you also bring in the unitarity loss and compare, you also see that there is a strong correlation between the fidelity index and the unitarity loss. So now let me go back to these plots in the linear and quadratic moduli case. And now, again, I don't have access to the unitarity loss, so I'll plot the fidelity index. And the fidelity index does exactly, well, at least approximately, does what I wanted to do. It isolates an island of good predictions. And this island is very close to the expected one. Here is the plot I had before. This is the plot I had before here. But now I show you the even better plot of Zyboedov and company. It's basically the same plot. The loss is much better because they're solving a dedicated problem for every B, where we trained only once. That's the main difference, but otherwise it's very similar. Also notice that this is more granular because every time they have to resolve the problem again and again, whereas we can evaluate immediately. Okay, good. Now, if I show you the quadratic case, it's even more interesting. This is a harder case. I'm finishing in 3 minutes. So this is an even harder case, even for the pin case. When psi mu becomes larger, they have harder time to find solutions. Notice what was my plot was this one. It had this region and basically nothing else, no other feature. These guys find more features. They find this feature, they find 2 islands here, and then this curve here. Then they realize that these points here are spurious. They're basically some configurations, some scattering amplitudes that are numerically, they happen numerically to be close. They're finite partial wave expansions, but they happen to be close to these quadratic ones. So they shouldn't be there, but for some numerical accident, they are there, they are detected. But these 2 islands are actual solutions. They're in fact finite L equals 2 scattering amplitudes that have a quadratic B. What did the neural operator with a fidelity index do? It has a very similar thing like this one, but now it actually managed to detect also the other 2 L equals 2 features. So the presence of the fidelity index not only gives you reliability on when you should accept or reject a solution, but seems to also have affected the qualitative features of the prediction. Okay, and then you can do also some things with ambiguous phases. I will skip that. You can see the lectures if you want, or the paper. So this was just an example, just to give you a flavor of the different things we can do. So what was interesting to me here is not to solve this particular equation. I did not contribute too much to the existing knowledge. What is interesting is that I try to solve the equation without using the equation. And in many cases, we do not understand the structure well enough to solve the corresponding equation. Okay? So there are many more things to explore. For example, a couple of days ago, there was a paper by Lance Dixon who is using transformers for the first time to study the amplitudes bootstrap. And notice the paper is not in the HepTH, it's in the computer science section. There is a reason I think other fields have adopted these methods much more quickly than us, and I think there's an obvious reason for that. Our field is not naturally data-driven. It requires rigor and integrability. These are things that we like. ML methods, as you also saw in some of the examples I gave, are usually stochastic and error-prone. But I should emphasize that there are examples of rigor and interpretability in ML and AI. And I invite you to see a recent Perspective article on this, emphasizing this point by Gukov, Halverson, and Rille. What is most exciting to me here is not that I will have some new numerical method to get numerical results. I'm more of an analytic person. What is exciting to me is that I'm trying to apply unorthodox approaches to a challenging mathematical and physical problem, and this, unlike other fields, doesn't happen automatically. It will require us to rethink the kinds of the problems we're trying to solve and reformulate them, and that, I think, might lead to considerable conceptual gains. Non-perturbative QFTs pose a plethora of such challenging problems, and it's mostly an unexplored area with these methods. This is my last slide. And personally, I find the conformal bootstrap a particularly interesting context to apply such methods because it is genuinely a non-perturbative approach. And I will end with 3 questions. Can we bring together the progress of recent years in SUSY QFTs, ADCFT, analytical numerical bootstrap, integrability to devise new strategies and to extend, generalize the knowledge of tractable corners into generic inaccessible regimes? That will give even higher value to the stuff that we are already doing. Another more specific question, can we use ML and AI to improve the numerical bootstrap on the technical front? It's already reaching a stage where it's becoming harder and harder to do higher multi-correlator bootstrap calculations. How will the interplay between numerics and analytics evolve? Another question, can we apply similar methods to more general QFTs? The S-matrix bootstrap is an obvious target. And I'll stop here. Thank you.
Thank you very much. Questions?
Thanks for a nice talk. I don't know if this is a meaningful question, but I still ask it. So, in your example, what's sort of the dependence on the L values that you train your data on? You chose L equals 1, 2, 3.
Yeah, the reason why we chose, in the beginning we tried more L's, but if you plot higher L's, you will see that they are they are functions that have lots of kings and they are almost discontinuous, and it made learning much, much harder. So we went up to L equals 3 where it was sensible. I mean, it still has kings and stuff, but not too complicated, and that's why we trained up to L equals 3. But one could try to, one thing that I try to emphasize here is that you get this neural operator, you get this fidelity index or whatever, which is quantity. I like to view it as some new neural network motivated some new parameter, okay? But it doesn't depend only on the physics, it also depends on the learners you used. So it's like you're trying to solve a problem, and then you have 2 groups or 3 groups, and some people, group 1 learns this kind of thing, group 2 learns this thing, etc. So you get these quantities that depend on the learners. So you could try to do a different type of training with different hyperparameters, different samplings, etc. You would, I think, get a different, you will extract different information from the problem.
Okay, thanks.
There's another hard problem in quantum mechanics, reconstructing the potential from unknown amplitude. Has anyone tried to do it using machine learning?
I don't know. One can try. Yeah. That's indeed an inverse scattering problem. Yeah. One could try all sorts of different things. You can try.
More questions?
For physicists to solve a system. So suppose you have all this nice method, you get some results, but unless you have some ways to interpret this result or to have some simple model that explain it.
That's right. Yeah, that was this point here. It's not always, interpretability is not always obvious here. So it requires further work.
Which you cannot do using this AI and...
Well, we don't know yet, right? Because if you ask ChatGPT, you get some answers that surprise you. So, so it's clear that this thing at this moment, in some sense, it's not very impressive, right? Because the whole AI business, ML business, is mostly about fitting things, right? But now it's reaching a level where this fitting becomes impressive and it's highly non-trivial. So what will happen in the future is not clear. Interpretability, there are mathematical problems like Magdalena was talking about, an example where you actually get you identify some structure. It's not clear what, if this is an actual conjecture. It makes a conjecture in mathematics, and then you bring in the human in the loop, and then you get interpretability. All these are part of the game here. But I think what is most interesting to me is the fact that in order to use these methods, we cannot just use them like astrophysicists. They just do signal analysis, right? They just take these methods, they do a standard thing. In our case, we have to rethink how to posit the problem, and also, what kind of analytics or extra numerics are we going to use to make the search better or the problem better defined? And that, I think, is a very useful exercise.
Any more questions? All right, if not, let's thank Vasilis again. And our last speaker is Marcos Marinho, who's coming to the stage. There you go. On resurgence and...
Okay, let me first thank the organizers for the invitation to come into Padua. I have this dubious honor of giving the last talk, so I will try to be fast because everybody wants to... sorry, I have to turn on this way. So I was thanking the organizers for invitation to Padua, and I will try to be fast because everybody wants to finish this conference, including myself. So, many of the things I'm going to say today have an overlap with what Zoltan was explaining yesterday, but I think it's important to go through interesting things a couple of times. So my starting point here is going to be very traditional, it's going to be perturbation theory. I mean, we like perturbation theory because it's a universal tool, it's analytic, but perturbation theory has an original sin, which is it never gives you the exact, it almost never gives you the exact result for an observable, because perturbation theory gives you only asymptotic approximations to observables. So you want, for example, to compute the ground state energy in a quantum mechanical problem as a series in the coupling constant, you will find that the coefficients grow factorially, so this series is asymptotic and is not really representing a function. So this is not, you cannot really even write a sign of equality here. You only have an asymptotic approximation. And the asymptotic character of the series is related to the existence of non-perturbative effects in quantum theory, which go typically beyond perturbation theory, and they are exponentially small more often than not in the, in the coupling constant. So the typical non-perturbative effects I will consider here, and the ones that we really find experimental in quantum field theory, are exponential effects in e to the minus a over g, where a is a constant, and you see that this is non-analytic when g is equal to 0, and this is invisible in conventional perturbation theory. So what do you expect is that if you wanted to compute a physical observable, you would have something like this. You would have to add the knowledge, the perturbative knowledge that you have, and then you should add some exponentially small corrections. And this actually is the answer that is suggested by the saddle point method when you apply it to the path integral. So if I write this equation explicitly, I would write my observable as the perturbative series I had before, plus a bunch of exponentially small corrections, which, by the way, involve themselves infinite series in the coupling constant. So you have an exponentially small term here, which is non-analytic, but then it will be multiplying a power series in G. And this is the kind of picture that you would find as saddle point approximation. So you could think about the perturbative series as coming, say, from the leading saddle point, and then additional saddle points would give you this kind of additional term. Okay? So this is roughly the idea. But of course, this idea has to be qualified in many ways. But the most important thing is that this kind of fundamental object that includes the perturbative series plus this non-perturbative part is something which goes beyond traditional series, has a special name, which we call trans series. Okay? So this was a term introduced by Jean Eccal, which is the mathematician who formalized many of these things. And what is very surprising about the trans series is that, if you think about it, is that we know how to calculate the perturbative part because our main quantum field theory textbooks have many chapters on doing renormalized perturbation theory, but there is no chapter in our textbooks about how to calculate the exponentially small corrections. I mean, there is no chapter in Peskin and Schroeder which tells you how to calculate this. You have many chapters on how to calculate this, but it's natural to add these two things, but you don't really know how to do this. And this is just I can already tell you what is the fundamental challenge here. The fundamental challenge because this is a conference on fundamental challenge in theoretical physics. The fundamental challenge is to develop a systematic theory of non-perturbative effects and transeries in such a way that when you get this transeries and you manipulate it correctly, you will get actually an exact equality, an exact result for the observable, not just an asymptotic approximation, but an exact result, okay? And this is the program that many people have started. It's sometimes called the Resurgence program. Also, I will qualify this in a little moment. But before telling you what are the challenges ahead, let me just give you a brief review of what is known. What do we really know about non-perturbative effects and transeries in quantum field theory, for example? As I said, this is not really chapters in the standard books, but this is really an old problem. And this problem was already started, people started to think about this problem already in the 70s and 80s, so this is really a traditional problem in theoretical physics, but I think it's still not completely clear how to go about it, and I will try to give you a perspective on this. Okay, so there is a first tool that I'm going to use in order to have some knowledge about non-perturbative effects. And this is one of the things that Zoltan was explaining just today. It turns out that one way of learning about non-perturbative effects in physics is by using perturbation theory. And the good thing about this is that this can be made mathematically very precise, and since I'm a mathematical physics, I like this type of problems. So I'm going to give you in a very short summary of how this goes, and this repeats many of the things that Zoltan explained yesterday, but I'm sure that we wouldn't mind going through them again, because it's relatively complicated. So let's suppose that we start with a formal power series, which has coefficients an, which diverge factorially. So this series, as I said, doesn't really define a function. This series has zero radius of convergence, so you don't really know what to do with it. And as Zoltan was mentioning yesterday, what you can do is to do a Borel transform. This is a radical surgery operation in which you divide every coefficient which goes factorially by n factorial. So these coefficients now, after divided by n factorial, will typically grow only exponentially. And then you introduce a new variable, so introduce a new function, and this function is going to be convergent in a neighborhood of the origin, typically. So this is fantastic because you go from the uncontrolled walls of asymptotic series to the controlled walls of analytic functions. And if you look at this Borel transform, it's going to be analytic at the origin, but then once you move away from the origin, you are going to start to find singularities in the complex plane. And these singularities can be of all kinds. You can have poles, branch cuts, and so on. So generically, you expect something like this. So sigma omega here, omega is an index, so sigma omega prime, they know the position of singularities. And I want to emphasize that these are things that you can actually compute realistically if you know enough terms of your perturbative series. So this is a plot of the structure of singularities in an actual physical example. I think this comes from Cyber-Witten theory. But these are things that you can really calculate, and you can see the position of the singularities by doing numerical calculations. So this is not something abstract, it's something that you can really implement. Now, once you have this, it turns out that these singularities are really crucial for the game, because these singularities are going to have the information about the non-perturbative effects. And what you have to do, I mean, I'm not going to give you the details. Zoltan tried to give some of the details yesterday, but it's really slightly complicated. But the main message of this is that the local structure of this Borel transform around these singularities has information about new sectors of your theory. So essentially, a local analysis of the Borel transform of each of these singularities will give you two pieces of information. It will give you a new power series that I denote here by phi omega z. And if you normalize this power series correctly, you will have some sort of overall constant, which is going to be important in some of the applications, which is called sometimes Stokes constants. And these are information that is intrinsic to this Borel transform. So if you know the perturbative series in enough detail, you should be able to extract this information. Okay? So this is local information of the Borel transform that you can find with complex analysis. Now, once you get this information, you build up a non-perturbative object, which is simply an exponential of the location of the singularity divided by z. So this is the non-perturbative effect that I was mentioning before. Then you will have some sort of loop expansion around this effect. And then you will have an overall strength of this series given by this Stokes constant. And of course, this Stokes constant depends on how you normalize this series, but sometimes there are natural normalizations of this series which give you natural normalization for these Stokes constants. And so, and what I want to insist that this is a well-defined mathematical problem. You take your favorite power series in your favorite quantum field theory, in your favorite string theory, and this problem is with very mild mathematical assumptions. It's a problem that can be solved. Okay? You can actually find all these series, and the collection of power series and those constants that you find in this way is what we call the resurgent structure of the perturbative series. Okay? One way to get this information is by looking at the large order behavior of the perturbative series. It can be very easily seen that this information about the singularities is equivalent to knowing the large order behavior of the perturbative series. But this is a well-posed mathematical problem. So one mathematical challenge is, given your favorite theory, how you would extract all this information. But what we are interested in here is what we can know physically, what we can learn physically from this structure. Okay? So this is, as I said, this has a long history that goes back to a very nice paper by Bender and Wu in 1971, where they tried to solve this problem in the simplest context possible, which is ordinary quantum mechanics, stationary perturbation theory in quantum mechanics. So they look at the simplest problem in perturbation theory in quantum mechanics, which is the anharmonic oscillator. So you have a harmonic oscillator here, and then you perturb with a quartic term, and you can compute, for example, the ground state energy of this system by a power series in G, and this is an exercise that we regularly give to our students in graduate courses in quantum mechanics. So, as I said, this is a well-posed mathematical problem. What is the resurgent structure of this series? And actually, Bender and Wu essentially solved this problem with a mixing of numerical and analytic techniques, and they found that there is going to be a singularity in this Borel plane, in this Borel transform, of -1/3, so there is going to be an exponential term e to the 1/3g's, and notice that this is positive with a prefactor, and then there will be an additional power series that I didn't write here. So what's the meaning of this? What's the meaning of this trans series term, this non-perturbative thing? Well, this is actually a signal of tunneling in this problem. Why? Because if you change the sign of G, and this potential will go back, and then the ground state will be unstable, and it will tunnel, okay? And there will be a beta value KB effect that you can compute, and you see when G is negative, this becomes an exponential of something negative, and this is actually the exponential rate of decay for this problem. So you can discover non-perturbative effects like tunneling, which is the quintessential non-perturbative effect in quantum mechanics, by doing this game. Okay, so this is in a sense the simplest example, and we already learned something. If we didn't know about tunneling, you would have discovered it in some way by doing this analysis here. Okay? Now, finding the resurgent structure of a given series is a well-posed problem, but very challenging. Now, in realistic field theories, one question you can ask is, what do we know about this problem in realistic field theories? Now, we have only hints of this structure, and usually are based on approximations, like, for example, large N. Now, one thing that, so as I said, this is a traditional problem which goes back to the 70s, but one thing that we have learned in recent years is that maybe we can try to make progress in this type of problem by looking at sufficiently simple quantum field theories. For example, topological field theories are a good candidate to try to understand this, because topological theories, in some cases, we have control over the perturbative series, and at the same time, this is sufficiently simple as to make progress in this. And another place in which we can try to understand things is integrable, for example, two-dimensional quantum field theories, and this is something that Wagner was telling us about yesterday. So let me tell you a little bit about what you can actually learn in solvable examples. So I'm going to give you an example quickly, an example in topological field theory. So the topological field theory, which has a nice perturbative expansion, is Chern-Simons theory. So I'm going to give you an example in complex Chern-Simons theory. So you can now take complex Chern-Simons theory, which is a gauge theory in 3 dimensions, and you can do a standard perturbation theory around the trivial connection. Okay? So the trivial connection will have a perturbative series in the coupling constant, and it turns out that this expansion should tell you about non-perturbative sectors of the theory. And it turns out that in this case, you can actually see that if you expand around the perturbative connection and you try to see this non-perturbative structure, I'm choosing here a very special example where I do complex Chern-Simons theory on the complement of this hyperbolic knot. So this is an open 3-manifold. Now, you can actually find the resurgent structure in this example very explicitly. You find towers of singularities here. And what is very beautiful is that these singularities the location of these singularities, which, remember, is the strength of the exponential effect that is going to be associated to them, is the volume of the hyperbolic manifold, which is the complement of this knot. So this is actually non-trivial because this is the action of a gravitational instanton in complex Chern-Simons theory. This is the connection that represents the complete hyperbolic metric on the complement of this knot. So you really learn about new non-perturbative sectors of this theory by looking at the trivial perturbation theory. And this case is even more exciting because you can actually guess or compute the Stokes constants, and they turn out to be integers related to BPS state counting. So these Stokes constants that appear in the problem that I was mentioning before, it turns out that in topological field theories have a topological meaning. They are integer invariants counting objects in actually a dual supersymmetric theory to here. And this is actually some new insights that came in the theory of resurgence by applying to this type of samples. Theory of resurgence is an old theory that comes, as I said, from the 70s. By applying to new topological models, you can learn things that are quite surprising. You can actually, in a sense, discover new topological invariants by doing this type of analysis. Now, what can we learn from this study from resurgence? Now, one thing that we learn is that instantons, non-trivial saddle points of the path integral, are a source of non-perturbative effects. This we knew before. It's confirmed in the example of quantum mechanics that I showed you, that I just showed you, and it's confirmed, for example, in this complex Chern-Simons context. But one very interesting lesson of resurgence is that it shows you that in many realistic field theories, there are non-perturbative effects, there are Borel singularities associated with Borel singularities, which are not due to instantons. This is a very important point that people who have worked on QCD know very well, but people who have worked on string theory are maybe not as familiar with. And these additional Borel singularities are sometimes called renormalons. And in QCD and in other asymptotically free theories, the resurgent structures associated to renormalons are able to detect non-perturbative effects which are not due to instantons, which are due to vacuum condensates. Okay? So they are due to non-trivial vacuum expectation values of operators in the vacuum of these theories. So let me give you, again, a very simple example. So imagine that you consider, you can do it in QCD, but you can also do it in simpler theories like the Gross-Neve model. Suppose that you calculate the quark self-energy in a theory in which you have fermions interacting with some other field. This could be this line. So you have this is a quark self-energy, so you have a quark anti-quark two-point function, and here you have an interaction of this quark with some other particle. It could be a gluon, or it could be a scalar particle in the Gross-Neve model. And these type of diagrams, you can see that they lead to a Borel singularity. So they are diagrams that appear in perturbation theory, will lead to factorial growth, and they will lead to a Borel singularity. And the corresponding non-perturbative effect is actually related to a quark condensate, to the fact that quark anti-quark operators have a non-trivial vacuum expectation value in this theory. And this, of course, in QCD is very hard to test, but recently with Ramon Miravillas, who is here in the public, we actually verified this very explicit in the Gross-Neve model, which is a toy model for the quark sector of QCD. But the general lesson is that when you look at these Borel singularities, you will find things which are not telling you about additional saddle points of the path integral, they tell you about other things. So let me now make a warning, a very important warning. So far, I have told you how to use the behavior of perturbation theory and these Borel transforms to learn about non-perturbative effects. But it's very important to notice that not all non-perturbative effects can be detected by these resurgent structures. There are non-perturbative effects that are totally invisible when you look at perturbation theory. And there is a very simple example, which are theta angle effects. So theta angle effects are totally invisible in perturbation theory. And for example, you have an instanton that couples to the theta angle, you will never see this in perturbation theory. So resurgence is a powerful source of information in the construction of a theory of transeries. But it's not the whole thing. It's just a method of detection, a very important one, but it's not really a theory of non-perturbative effects because we know that there are non-perturbative effects which are going to be missed in this way. Now, when people try to go beyond perturbation theory already in the 80s, there were actually two theories that were proposed to do this. And you have probably been exposed to some of these theories. One of them is instanton calculus, and the other is what I would call condensate calculus, which was introduced by Shifman, Weinstein, and Sakharov, mostly in QCD, to actually calculate effects due to vacuum condensates and so on. Now, these theories are very impressive. They have obtained some very successes, some important successes. But my feeling, and that's why I'm giving this talk, is that they are probably incomplete, they are insufficiently tested, and I think they are not fully understood, as I will argue in a moment. And remember, I want to make some connections to people that have talked before in this conference. Jan de Boer was mentioning how, in doing calculations with instantons in gravitational theory, sometimes one has to consider off-shell configurations, and this was not very clear. He was asking, what are the rules of the game for this? Actually, off-shell configurations in instanton physics are generic. Even in quantum mechanics, if you want to consider multi-instanton configuration in quantum mechanics, you have to consider off-shell configurations. So the rules of the game for doing instanton calculus are not really even, I would say, completely understood in quantum mechanics, not even to think about quantum field theory. So I think it's really important to revisit these things because we talk about instantons, but sometimes we don't really know very well what we are talking about. Yes? Sorry? Yes. In perturbation theory, you will not see it. In perturbation theory, around the trivial vacuum, okay? Okay? That's a fact. Also, effects due to chiral symmetry breaking are not visible in conventional perturbation theory. Now, let me make a remark about string theory. So, the genus expansion in string theory not only grows factorially, it grows doubly factorially, and this is something that we know due to the work of Gross and Peribal and Schenker. So resurgence, the techniques of resurgence should be also very useful in string theory and should give you information on non-perturbative effects. And this was actually one of the motivations for Polchinski to introduce D-branes. One of the reasons that Polchinski introduced D-branes was that this was going to be a source of non-perturbative effects in string theory. Now, there are many interesting results in the case of non-critical strings, and this has also a long tradition, starting with works by Saint-Just, Hénard, and other people. And recently there have been many impressive progress by Ricardo Schiappa, who also here in the audience, and his students, where they have actually, in a sense, fulfilled the full program of computing all the Stokes constants in non-critical string theories. And there is a more complicated theory than non-critical strings, where there has been a lot of progress in understanding the resurging structure, and this is topological string theory in Calabi-Yau manifolds. And I don't have the time to talk about this here, but I will talk about this in Strings 2024, if you are going to attend or you want to see the conference. So I will give you more detail. I will give more details about this in that talk. But one thing I can tell you is that we have a conjectural complete description of the resurging structure of topological string theory on any compact or non-compact Calabi-Yau, and we know exactly we have a conjectural prediction for where are the singularities, what are the transitions, and so on. So there is a complete conjectural solution for the problem of finding the resurging structures in the case of topological string theory. Okay? Okay, so this is in a sense what we know, and let me now try to pass to I want to make now a self-criticism session, because I think it's very important when you propose a program to be able to reflect why do you want to do this, right? I mean, this is something that we should all do at some point. You know? Why do you want to do what you are doing, right? And I think that's important. So why do bother about all these transseries? And after all, you could go non-perturbatively without doing any of this. You can do a more direct approach which avoids perturbation theory completely. And you can do lattice, and we have heard today about, for example, using machine learning tools in quantum physics. Why should you bother about all these perturbative series and completely different series? Just go directly to the lattice or go directly to the bootstrap and so on. Okay, let me give you 3 reasons why there is still maybe interesting to do what I'm proposing. Well, the first reason is that transseries are intrinsically analytic objects. And sometimes we can even do back-of-the-envelope calculations. So if you take a person who is working in QCD, she or he will be able sometimes to give you an estimate of non-perturbative effects in QCD by doing a back-of-the-envelope calculation using resurgent techniques. So this is still important. We can do analytic techniques, analytic calculations, and sometimes they are very simple. Now, a very important reason for me is that resurgence gives you a semi-classical decoding on non-perturbative physics. When you look at the transseries, you know what are these things. The perturbative series is something that you can think about in terms of small perturbations around the vacuum. So they are like implemented through Feynman diagrams. Then, instantons or condensates, you can also visualize them in some way. So we have pictures for these things. And this is also related with what Alejandra was also mentioning yesterday. Remember that she was giving these partition functions for minimal models and so on, and she was decoding these partition functions in terms of a gravity theory. So you have this kind of box coming from the 2D CFT, which are these sums over characters, but then you decode these as a sum over saddle points in gravity. This is the kind of semi-classical decoding that resurgence gives you. And the third reason, and this is beauty is always in the eye of the beholder, but resurgent structures are really fascinating mathematical objects. I mean, the structure of transeries appearing in the Borel plane, all these Stokes constants that sometimes can be integers, can be topological invariants. This is really a fascinating mathematical problem which links complex analysis with the theory of resummation, with sometimes geometry and topology. It's really very fascinating. And remember, we have heard a lot about using computers in physics, and I'm the first one to use computers in physics, but also remember what Wigner said when he was shown a calculation from the computer. At some point, there was a computer, calculating some spectrum in quantum mechanics, and they gave Wigner the result of the calculation, and Wigner looked at it and said, well, it's very good to know that the computer understands the calculation, but I would like to understand it, me too. So let me now run some challenges for the future. Now, instanton calculus, as I said, I mentioned all the problems with instanton calculus. We understand it very well in supersymmetric theories. And one of the reasons that we understand very well instanton calculus supersymmetric theories is because at some point we had an exact model for instantons, which was Seiberg-Witten theory. Seiberg and Witten predicted the whole structure of instanton sectors in n equal to super-Yang-Mills theory. And using this, there were a lot of activity, and this culminated in the work of Nekrasov, which gave a full microscopic understanding of this. Now, the problem is that in realistic quantum field theories and non-supersymmetric quantum field theories, we don't have such a toy model. We didn't have such a toy model until very recently. And I want to propose, in a sense, what I think right now could be the analog of Seiberg-Witten theory for non-supersymmetric theories, and this is the O3 nonlinear sigma model. And in the O3 non-sigma model, you can actually calculate, I think Zoltan was talking about this, you can calculate this free energy in the presence of a chemical potential. And recently, using integrability, instanton amplitudes have been decoded from the answer from the Bethe ansatz. So we have now a very explicit prediction for instanton amplitudes in the O3 non-sigma model. And I think it's a non-trivial challenge to reproduce this with instanton calculus. I mean, they are going, here you will face all these problems. You are going to have to consider off-shell configurations and so on. I don't know how to do this calculation in detail, but I think this is really one of the challenges for the future, in understanding instanton calculus correctly. If we want to apply in gravity, we better understand it before in quantum field theory, and this is a proposal for how to go. Now, condensate calculus. This is the other alternative to non-perturbative effects. This has been extensively used in QCD phenomenology, and it should also be able to explain renormal singularities in general QFTs. But there have some hints in the literature that you might need a more general theory, in particular in calculations that we have done with Ramon and that Zoltan has also done. We have found that in some cases there are singularities appearing in the Borel plane which are not really fitting into the pattern that is expected from the theory of condensates of LBZ. So I think we really need to develop condensate calculus in these and other models, and maybe we have to generalize these ideas, and maybe there are non-perturbative effects which are not really accountable neither with instantons nor with condensates. So this is also something to consider. And so far, this is my last challenge. So far, I have focused on the coupling constant expansion. But what is very interesting is the 1 over n expansion. The 1 over n expansion is also an asymptotic series, which also will have 1 over n exponentially small corrections in 1 over n. And these are very important in string theory, and in particular in the context of the ACFT correspondence. But we don't know very much about the non-perturbative structure of the 1 over n expansion, except in the very simple case of matrix models. So one question is, can we use all these ideas to understand the non-perturbative structure of more complicated string theories? And maybe if we solve this problem of the 1 over n expansion in QFT, maybe with the help of the STFT correspondence, we can understand more general string theories with ADS duals and so on. Okay, this is all. Thank you very much for your attention. Thanks for the very nice talk. Questions?
Question about the renormalons in supersymmetric theories. In n equal 2 theories, probably there are no renormalons. No? What about n equal 1? Do you know some examples?
I haven't
where
looked
they
at
could
it.
be yeah.
I haven't looked at it, but of course, you know, there are condensates in equal 1 theories. For example, there is the Gluino condensate and so on. So you might think that this leaves an imprint on perturbation theory you could like detect in some way. But I have to say that I have not really thought a lot about n equal 1 theories. This is something that I think should be done because it might be one interesting intermediate step between purely non-supersymmetric theories and theories in which all these things are essentially trivialized. Okay, that's absolutely the case. Yes.
Just a question, like in string theory, there's a classic example of the R to the 4 coupling, where using duality and symmetry, supersymmetry, we know the full non-perturbative result. Can you also understand this non-perturbative corrections to the R to the 4 couplings using resurgence?
I think this has been even done. I think there are people like Dorigoni and Michael Green who have looked at this kind of examples. So, I think, you know, in a sense, string theories on theories with home supersymmetry or theories which are sufficiently simple are the ideal testing grounds for resurgence, because this is where you will find, you know, that everything is recovered from perturbation theory. So the hardest examples are, of course, asymptotically inferred theories, even into dimensions and more realistic theories. Yes.
Okay. So maybe they're even sort of trivial examples,
What do you mean a trivial example?
No, I mean maybe this R to the 4 coupling is a trivial example.
No, I don't think it's trivial. I don't think it's trivial, and in particular, if I remember correctly, but you know, I haven't really studied this in detail. But I think there is also a very interesting interplay with modularity, for example. So this is something that people have also tried to understand. You know, you have to sort of imagine they have an S-duality structure. You know, you have a duality between tau and minus 1 over tau. You know, what does this imply for the resurging structure, right? This is a natural question because it has to be a constraint on the non-perturbative structure of the theory. So there is now a lot of also work in the direction of putting together resurgence and modularity constraints, which I think apply to this example that you're mentioning. Yes.
Thanks.
This question about something you mentioned in the last slide. What determines the singularities of 1 over n expansion in field theory?
Well, the singularities, I mean, as I said, the only example which we know very clearly is like matrix models, okay? So matrix models is another story that eigenvalue tunneling gives you large instantons. Now, there is a source of exponentially small corrections in the 1 over n expansion, which is just the Larchen, what I would call the Larchen dressing of a conventional instanton. If you have an instanton in a quantum physics with a Larchen expansion, you know, it goes like e to the minus 1 over g, and then when you go to the top coupling, it goes like e to the minus n over lambda. So this is the first term in the action of a Larchen instanton, which goes like e to the minus n times a non-trivial action of lambda. So in Larchen theories, one source is just, in the same way that to get the planar free energy, you have to resum all the planar diagrams, you have a conventional instanton, you have to resum all planar diagrams in the background of an instanton, and this gives you a Larchen instanton, okay? So this is a source of non-perturbative effects in Larchen theories. And in particular, Larchen instantons in matrix models are an example of this. But we don't really know very much about it. That's one source, but there could be others.
You said that in the case of this instanton business in QCD, you found there's a mismatch between position barrel singularities and those condensates?
Not in instanton, renormalons.
Excuse me, yes.
Yes.
So the position of barrel singularities in the case of QCD is
there is a general story that position of singularities, of renormal singularities, is an integer number divided by beta 0, right? Okay. Now, this is a very explicit calculus, and Zoltan can tell you about it, because it's actually, you know, from the TVA equations you can see very clearly that the location of singularities when you calculate the free energy in the presence of a chemical potential for integrable models is not there. Most of the singularities are not located there. Okay.
That's my question.
Yes.
But my question is that position of various singularities and one-to-one correspondence with OPE structure.
Yes, exactly.
So are you saying you get something which contradictory with OPE?
No, not contradict directly, because this observable is in principle doesn't have an OP, it's a free energy. So it's not a product of operators.
But free energy has a lot of ambiguity inside.
It has?
It's ambiguous quantity, depends how you regularize the short distances.
Yes, you have to do an additive normalization, and this might be the source of this. There are many people who are now trying to look at this problem. One way, for example, there is work in progress by Marco Cerone and Thomas Reis, when what they are saying is that this chemical potential acts like a mass, and then the beta zero gets changed because there is some sort of cutoff set by H, and then you have to, in a sense, this gives some sort of mass to some of the particles, and this changes the value of beta zero and so on. So there are some sort of explanations around it, but I think what one should be able to do is a real direct OP calculation of these new non-perturbative effects. That's something that still has not been done.
But you believe, let's say, if I go from free energy to the correlation function, when you have very quite precise control of OP, those new singularity will reappear or not?
That I don't know. I want to leave this possibility open. I mean, I know that the OPE doesn't predict this, but I think the OPE has to be really, I mean, there are many few tests of this OP idea. I have to say that there are very, very few tests of this OP idea where you really know the answer and you can reproduce it with the OP. I mean, people have used the OP, but people have not really, not to my taste. I'm a mathematical physicist, okay? So I'm very picky, okay? So for my taste, there are still not sufficiently good tests of this idea of the OP. And recently with Ramon, we wrote this paper with a test on Gros-Neve just to make sure that things work correctly in a two-point function, and there it works very well. But I still think, you know, that this idea should be really tested in more detail in examples.
Once you mentioned Shifrin-Weinstein-Zakharov.
Yes.
Many years ago, they looked for the question, how does OP look like in Minkowski Euclidean space?
Yes.
And there's this claim, which hasn't been verified yet, and the structure of Barrett singularity will depend on the signature. It may happen going from Euclid to Minkowski space.
Yes.
In Minkowski space, we may have new singularity which is not visible in Euclid.
Yes, this is related to this quark-hadron violation of quark-hadron duality, right? Yes, this is actually related. I mean, this actually raises. I mean, let me reformulate this in a kind of more general way. I think the main problem there is that, you know, you have all these trans-series. You have the perturbative series, the trans-series, but you might have an infinite number of trans-series. So if you do a resummation of each of these trans-series, you get usually a well-defined number, but you still have to sum the infinite number of trans-series, and this is still not clear that this sum is going to be convergent. So there might be another source of infinities apart from the factorial divergence, and this is actually related to this quark-hadron violation of quark-hadron duality that you were mentioning, and this is actually something which we still don't know very well what is going to happen and what are going to be the techniques to address this. Okay? So this is actually a deep problem from this program, in the sense that we have at some point to address this problem as well. Now, in some examples, like for example the integrable models that we have been studying also with Zoltan, this problem does not arise. The trans-series sum is convergent. Okay? Or we have indication that it's convergent. So in that case, this problem will not arise. But in more realistic case, it might arise, and we might need a further generalization of this framework. Absolutely. More questions? Yes?
Just in the context when you describe your complex Chern-Simons and you have your Stokes constants to represent integers, and you say this is related to the BPS counting problem.
Mm-hmm.
Do you think this is applicable? Can this be helpful in the index computations?
In the?
Index or superindex?
Actually, these BPS integers are an index. These BPS index, these Stokes constants are the coefficient of an index. And this was one of the kind of surprising discoveries for us, that, you know, those constants, which look very crazy because they are these numbers that appear when you do this, eventually they make up an index.
But this applies just to this complex Chern-Simons, or this
actually,
is just topological class?
It also applies to topological string theory on Calabi-Yau. There also, the Stokes constants are integers. Of course, this is not a universal feature, and for example, Ricardo and his collaborators have calculated the Stokes constants for Pauli 1, which describes 2D gravity, and there the Stokes constants are far from being integers, are all irrational numbers. So this is very specific to some types of theories. But it would be very interesting to know for which theories you have this sort of integrality properties and for which theories you don't have it.
One at holds. I see. Yeah.
One last question? Well, if not, let's start Marcos again.
Okay, let me just say that I think it's a good moment now, because it's the end of the conference, to thank Alessandro and all the team for this wonderful conference.
Well, thank you very much for coming, and thanks to all the speakers for the very nice talks that really made this conference very, very interesting. And I hope we will have a lot of progress in the 4 years of the action along all these lines. Couple of last announcements. There is lunch where we had the coffee break, so please enjoy and continue your discussions. And finally, if you want to keep your lanyards or souvenir, you're very welcome to. If you're full of lanyards, you can leave them at the desk and we will recycle them, use them for the next event. I think that's all, so enjoy. Thank you for having come.